The edge of space isn't a wall, it's a horizon, and it's moving away from us at the speed of light. Go far enough, and the universe doesn't just get darker, it starts erasing its own past. So what's beyond that fading edge? More space, the limit of time, or a boundary where reality itself breaks? There is a moment above Earth when the familiar world turns alien, and every instrument begins telling a different story. In that thin, silent climb, up stops being a direction and becomes a question. What we call an edge is rarely a line. It is a change of rules, a shift in what can exist and what can be known. The air that once carried sound becomes too sparse to hold it, and the sky's color drains away for reasons hidden in physics. Above that, heat can rise while warmth disappears, because temperature and touch no longer agree. From the start, this film treats boundaries as thresholds, measurable, contested, and alive. Some are drawn by engineers and lawyers who need a number that settles an argument. Others are drawn by fields and particles that do not care what we name them, only how they move. The most important edges are not marked on maps at all. They are written into light, into time, and into the limits of cause and effect. So we will begin with the nearest frontier, where the atmosphere breaks into stacked regimes and the planet's influence thins into plasma. We will watch the horizon curve and the glare sharpen, then follow the invisible architecture that still holds Earth together. A magnetic cocoon, sculpted by the sun, flexes and snaps, sometimes gently, sometimes violently, and the consequences can reach down to the systems we depend on. Then the perspective widens, and the voyage becomes a kind of forensic science. We track the sun's farthest reach as it pushes back against the interstellar medium, forming a boundary that breathes with solar seasons. We listen to spacecraft reports from the deep, where signals are faint, instruments age, and certainty is earned one reading at a time. Beyond that, the Milky Way refuses to behave like a simple island of stars. Its outskirts blur into halos and streams. Its structure is distorted by our position inside it, and its true mass is betrayed by motions that should not be possible. Something unseen dominates the galaxy's gravity, an influence that shapes the rim without ever lighting it. And when we finally lift our gaze from a single galaxy to the universe itself, distance stops meaning what it meant before. Looking outward becomes looking backward, until we reach an era where ordinary images can no longer form. The sky turns into a record of conditions, and faint patterns become evidence, clues to geometry, expansion, and the early universe's first imprints. From there, the journey turns even more abstract, but no less physical. We will ask what it means for space to have a shape, and whether a cosmos can be finite without having an edge. We will follow ideas that extend beyond what any telescope can directly resolve, carefully separating what is implied, what is allowed, and what is still pure speculation. Because beyond is not only a destination, it is a test of our best theories. Some proposals suggest hidden regions forever disconnected from us, not by walls, but by the way space-time itself evolves. Others imagine extra dimensions or new beginnings that replace a singular start with something stranger and more subtle. This documentary is an expedition through nested frontiers, each one deeper than the last. We will move from the edges we can approach to the horizons we can only infer, until we reach the boundary where explanations run out and new physics may be required. And through it all, one fact will remain. Every time we think we have found the edge, the universe offers another threshold and dares us to cross it. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We will climb from Earth's thinning air to the sun's last influence, then out to the galaxy's dark perimeter and the universe's farthest visible light. Past that point, we follow the mathematics of space itself, toward possibilities that challenge what outside can even mean. We start with an ascent that feels familiar, then quickly becomes alien. Air presses on the skin, sound carries with ease, and the sky looks endless above a curved horizon. At first, the world behaves like it always has, with wind noise and vibration translating motion into something your body understands. Then altitude climbs, and the ordinary cues begin to fail. Quiet arrives in stages, and the blue overhead starts to drain. That blue was never paint on the sky, and it was never a simple reflection. It is mostly Rayleigh scattering, the tendency of tiny molecules to scatter shorter wavelengths of sunlight more efficiently than longer ones. When the air is thick, sunlight ricochets through countless collisions, and the blue component spreads across the dome. As the air thins, the scattering weakens because there are fewer molecules in the path of the light. The color fades not because the sun changes, but because the medium between you and the sun is disappearing. Visually, the transition is unsettling in its clarity. The horizon sharpens as haze falls away, and distant clouds look like islands floating on a bright, curved sea. The glare hardens because there is less scattered light filling in the shadows, so contrast increases and edges look cut from glass. Above you, the sky deepens from blue to indigo, then to a violet black that feels too dark for noon. Eventually, the sky turns black overhead, not because night arrived, but because the air is almost gone. This is the first edge we can nearly touch, and it is not a wall. It is a gradient where flight becomes orbit and atmosphere becomes near vacuum by degrees rather than by decree. We call it the edge of space because language wants a line and stories want a threshold. Physics offers a transition zone with overlapping definitions, competing needs, and a stubborn refusal to end cleanly. In practical terms, one famous marker is the Kármán line, near 100 kilometers up. It is a convention used for records, treaties, and a shared global reference, because engineers and lawmakers need a number. The idea traces back to Theodor von Kármán, who asked when an aircraft must move so fast to generate lift that it effectively becomes an orbital vehicle. Above that height, aerodynamic lift becomes inefficient, and orbital speed matters more than wings. To stay aloft like an airplane, you would need to go so fast you're essentially in orbit. That statement hides a lot of mechanics, so it is worth unpacking. Lift depends on air density, wing area, and speed, and density drops dramatically with altitude. If density collapses, speed must rise to compensate, but speed brings heating and drag in ways that punish fragile structures. At some point, the most efficient way to stay up is not to push against air at all. You fall around Earth instead, continuously missing the ground because you are moving sideways fast enough. But other definitions exist because the atmosphere does not end at 100 kilometers. Some agencies use 80 kilometers, tied to early astronaut wings and historical precedent in the United States. That lower boundary reflects a time when reaching space was judged by experience and capability, not by global standardization. Others define space by orbital capability, not altitude, because orbit is an unambiguous behavior. Some define it by measurable atmospheric density, because density drives drag, heating, and how long a satellite can survive. Each definition answers a different question, and none creates a sharp, physical border. Are we talking about where a pilot needs a pressure suit, where a vehicle needs a heat shield, or where an object can complete an orbit? Are we talking about where the sky turns black to human eyes, or where molecules become so sparse that collisions are rare? A single word, space, is doing the work of several disciplines at once. The edge is real in experience, but fuzzy in matter. Even at 100 kilometers, there are still molecules, still collisions, still drag. Satellites in low orbit feel that drag as a constant, gentle braking force, and they slowly lose altitude unless they are boosted. The International Space Station lives in a region that is not empty, only extremely thin, where traces of oxygen and nitrogen still matter. Its orbit decays because the atmosphere swells and shrinks with solar activity, changing density at the same altitude. That swelling can be driven by ultraviolet and X-ray heating, which makes the upper air expand like a warmed gas. This chapter separates the poetic edge from the scientific edges. The poetic edge is a cliff where Earth ends and the cosmos begins, a clean cut between home and unknown. The scientific edges are thresholds where dominant forces change and where the governing equations shift emphasis. At one height, chemistry shapes weather and life in a thick, reactive mix of gases. Higher up, ultraviolet light breaks molecules apart and ionizes atoms, and the same air becomes something closer to an electrical medium. So we climb through layers that each behave like a different world, even though they are all part of one atmosphere. The troposphere is dense and turbulent, where water vapor, convection, and heat drive storms and clouds. It is the layer of weather, where rising warm air cools and condenses into visible structure. The stratosphere is stable by comparison, with temperature increasing with height because ozone absorbs ultraviolet radiation. That absorption is not just a statistic. It is a shield that reshaped life on land by reducing surface UV over geological time. Above that, the mesosphere cools and thins, where meteors burn in brief streaks as they compress and heat the air ahead of them. The light you see from a meteor is partly the object glowing, and partly the surrounding air becoming excited and ionized. Noctilucent clouds can form here, faint and electric blue at twilight, made of ice crystals in air so thin it feels impossible. Then the thermosphere warms again, not by touch, but by energetic radiation that deposits energy into sparse particles. The temperature can be high in a technical sense, even while the air would feel cold, because there is almost nothing to carry heat into your skin. Above that, the ionosphere forms, where sunlight strips electrons and turns air into plasma. It is not a separate layer you could point to with a finger, but a region where ionization becomes significant enough to change behavior. Radio waves bend and bounce there, which is why distant transmissions can sometimes reach beyond the horizon. Auroras flicker where particles collide, and the colors reveal specific atoms and molecules returning to lower energy states. The same sunlight that makes the sky blue down low makes the upper air electrically alive. The edge is not one line. It is a stack of transitions, each with its own rules, each one gradual and yet consequential. If you are watching from a capsule window, the layers are not labeled, but the visuals suggest them anyway. The bright limb of Earth becomes a thin, glowing band, and the atmosphere looks like a delicate shell. It is a reminder that the thickness of the air we live in is small compared to the planet's radius. Then comes another boundary that is less visible, but more powerful. Earth's magnetosphere is carved by the solar wind, a stream of charged particles from the sun that carries its own magnetic field. Our planet's magnetic field deflects much of that flow, shaping a protective bubble that is constantly being pressed and stretched. On the day side, it compresses under solar wind pressure, and on the night side, it stretches into a long tail. Inside this region, charged particles spiral along field lines, and some become trapped in belts that can persist for years. The magnetosphere is an edge because it marks a change in who controls the environment. Inside, Earth's magnetic field dominates particle motion, guiding trajectories like invisible rails. Outside, the solar wind dominates, carrying the sun's magnetic field outward and reshaping the plasma around it. The boundary shifts with solar storms, and it can be pushed inward during strong eruptions. It is not a wall, and it does not hold perfectly, but it is a moving frontier defined by pressure, fields, and plasma. From the ground, we talk about the sky as if it belongs to us. At the edge of space, ownership becomes a metaphor, and the atmosphere becomes a shared, thinning commons rather than a ceiling. The air that sustains us becomes too thin to breathe, then too thin to scatter light, and then too thin to slow a fast-moving craft by much. The black sky arrives while Earth still fills half the view, bright and textured with cloud systems. That contrast is the hook, because it compresses the familiar and the alien into one frame. This is where our central question begins to sharpen. When we ask what lies beyond the edge of space, we might mean beyond air and into vacuum, where pressure suits and sealed cabins become non-negotiable. We might mean beyond Earth's influence and into the sun's domain, where plasma flows and magnetic fields set the terms. Or we might mean beyond every familiar structure, beyond stars and galaxies, toward an edge of the universe itself. The same word, beyond, points to different maps depending on what you think the edge is. The documentary's tension is simple, and it does not resolve easily. We can travel to the edge of space with rockets and capsules, and we can watch the sky turn black in real time. We can cross the Kármán line and return with data, footage, and a clear record of altitude. But the phrase edge of the universe points to something else entirely. Something that sounds like a place, yet behaves like a limit. It invites a traveler's instinct, even though travel is not the point. To see why, we need to replace the idea of a border with the idea of a horizon. A horizon is not a fence in space, and it does not require a physical barrier. It is a boundary in what can affect us and what we can observe, because signals take time to travel. The most important edges in cosmology are not walls you crash into. They are distances beyond which information cannot reach you in time, no matter how powerful your telescope becomes. Light has a speed, and the universe has an age. That combination creates an observable universe, bounded by what light has had time to travel since the Big Bang. When we look far away, we also look back in time, because the light left its source long ago. Beyond that boundary, there may be more galaxies, more space, and more history, but their light has not arrived, and may never arrive, depending on cosmic expansion and how space itself stretches. This is the first hint that beyond can mean different things. Beyond the atmosphere means a change in pressure, chemistry, and the way heat moves, because convection stops when air is too thin. Beyond the magnetosphere means a change in fields and particle flows, because the solar wind becomes the dominant sculptor. Beyond the heliosphere means a change in the very medium between stars, where interstellar plasma and dust take over. Beyond the observable universe means a change in what can ever be known by observation, because the limit is written into time. So the universe presents itself as a layered set of edges, each one a threshold with new physics. Earth's atmosphere is a chemical edge, where life and weather operate in a narrow band of pressure and temperature. The magnetosphere is an electromagnetic edge, where plasma and fields negotiate control in a continuous tug-of-war. The heliopause is a stellar edge, where the solar wind yields to interstellar space and the sun's influence thins. The outskirts of the galaxy are a gravitational edge, where dark matter and sparse stars dominate the mass budget. These edges do not sit still. and they do not share a single definition. They are shaped by flows, forces, and time, and they respond to cycles like solar activity and long-term cosmic evolution. They are measured by instruments, not by intuition, with magnetometers, particle detectors, spectrometers, and careful tracking of orbits. Yet each one changes what it means to travel, to survive, and to understand. Each one also changes what here means, because here depends on what is controlling your environment. At the edge of space, the sky does not end. It changes state, and our senses lose their usual guideposts, because so much of perception is mediated by air. The black sky is not emptiness, only the absence of scattering, and the stars appear without twilight's gradual introduction. The silence is not peace, only the lack of air to carry sound from one surface to another. The boundary is not a line, only a regime shift, and that shift is the real subject. That is why this first edge matters. It teaches the pattern we will follow at every scale, from the thin shell around Earth to the largest horizons in cosmology. We will keep asking where one domain ends and another begins, and we will keep discovering that the ending is usually a transition. We will keep confronting the fact that the deepest edges are defined by limits on information. When the limit is time, not distance, the intuition of a frontier starts to break. Our hook is not that space is dark. Our hook is that the universe becomes stranger as the definitions get sharper, because precision reveals multiple answers rather than one. The more precisely we define an edge, the more we realize it depends on what we measure. Altitude, density, orbit, plasma behavior, magnetic pressure, and light travel time all draw different maps. Which map is real depends on what you are trying to do and what you are trying to know. So we begin close to home, at a boundary humans can reach, even if only briefly and at great cost. We use it to separate poetry from physics and to set the terms of the journey. The edge of space is where the sky stops being ours and where the next questions start. If the nearest edge is already fuzzy, what happens when the edge is written into space-time itself? Now we widen the scale without changing the question. We leave Earth's thinning air behind and enter the sun's expanding influence, where the environment is defined by a wind you cannot see. The next boundary is not drawn by altitude, but by the solar wind meeting the interstellar medium. We follow that pressure front, outward, toward the heliopause and toward the next meaning of beyond. We left the air behind, but we did not leave weather behind. Near Earth, space is still a shifting environment, shaped by fields, particles, and sunlight that never truly turns off. What looks like emptiness in a wide shot is, up close, a restless plasma landscape. Invisible forces braid together, and the braids tighten or loosen as the sun changes mood. The sun constantly sheds plasma as the solar wind. It is not a gentle breeze, but an expanding atmosphere that escapes the sun's gravity and races outward. In that flow, electrons and ions stream together, carrying energy, momentum, and electrical charge. Because the sun rotates, the magnetic field embedded in the wind is pulled into a spiral, an elegant twist known as the Parker spiral. That spiral matters because it guides charged particles like rails guide a train. Earth meets that wind with its own magnetic field. The field is generated by motion in the liquid outer core, where iron-rich fluid circulates and acts like a natural dynamo. As Earth spins, convection and rotation organize those currents, and the result is a global dipole-like field. It extends far beyond the atmosphere, reaching into space as a protective cavity. In daylight, it is compressed. On the night side, it is stretched into a long tail. Where the solar wind first feels Earth's obstacle, a bow shock forms. The flow is forced to slow and heat, and turbulence spreads through the plasma like froth in breaking water. This happens because the solar wind is often supersonic, meaning it moves faster than pressure disturbances can travel upstream. With no warning wave to smooth the approach, the wind must abruptly reorganize. Particles scatter, magnetic fields kink, and energy is converted into heat and chaotic motion. Inside, the bow shock sits the magnetosheath. It is a region of compressed, disturbed solar wind that batters the magnetosphere like surf. If we could see it, it would look like a cloudy, vibrating shell, eddies and ripples sliding around the planet. Magnetic field lines there are jumbled, and plasma density rises compared with the upstream wind. This is where the solar wind's orderly streaming becomes a rough, churning buffer zone. The magnetopause marks the main boundary of Earth's magnetic bubble. It is a pressure balance where solar wind momentum meets magnetic pressure, and neither side fully wins. On one side, the wind pushes with its bulk flow and its own embedded field. On the other side, Earth's field pushes back, resisting compression like a stretched elastic membrane. The magnetopause is not a solid surface, but it behaves like a boundary that can flex. This boundary is not fixed in place. During strong solar storms, it can be pushed inward, exposing satellites to harsher particle conditions and altering the safe corridors where spacecraft normally operate. When the solar wind's dynamic pressure rises, the magnetopause can move closer to Earth by several Earth radii. That shift changes the environment in minutes, not days, and it can bring the boundary into regions crowded with communication and navigation satellites. It is one reason engineers care about space weather forecasts as much as meteorologists care about storms. On the night side, the magnetosphere stretches into a long magnetotail. It forms because the solar wind drags Earth's field lines backward, pulling them into two lobes separated by a thin current sheet. In that sheet, opposing magnetic fields can be pressed together until they reconnect. Energy stored in the tail can snap and release in substorms, sudden reorganizations that fling particles toward the planet. The tail is a reservoir, and reconnection is the valve. Those releases drive auroras and radiation bursts. They remind us that near-Earth space has seasons, forecasts, and sudden hazards, even when the sky looks calm. Charged particles spiral along magnetic field lines and collide with oxygen and nitrogen high above the surface. The atmosphere responds by glowing, green, red, and violet curtains that flicker with the rhythm of the magnetic storm. In orbit, the same events can charge spacecraft surfaces and upset sensitive electronics. The beauty and the danger are part of the same physics. Space weather is not metaphor. It is measurable variability in plasma density, particle energy, and magnetic fields that can damage electronics, distort radio signals, and strain power grids. Magnetic fluctuations can induce currents in long conductors on the ground, a coupling between space and infrastructure. In the upper atmosphere, heating can increase drag, slowly lowering satellite orbits. Even GPS accuracy can degrade when the ionosphere becomes turbulent. Weather here is not about clouds, but about charged matter and moving fields. We call this region space, yet it still belongs to Earth's influence. The first lesson is that edges are defined by dominance, not emptiness, and dominance can be quantified. Which pressure is larger? Which particles are more common? Which field controls the motion? Those are the practical questions. In this sense, an edge is a change in rules. The same vacuum can feel like different worlds when the governing forces shift. Now we widen the scale without changing the question. We leave Earth's magnetic shelter and enter the Sun's much larger domain, where the wind is the atmosphere and the magnetic field is the weather map. The moon is not a gate, but it is a useful marker in our imagination. Beyond it, Earth's magnetic influence fades, and the solar wind becomes the main sculptor. Spacecraft begin to feel the sun more directly, not as light alone, but as a moving plasma ocean. Past the moon, the solar wind is still present and still fast. It fills the solar system and shapes every magnetized world it encounters, carving cavities and driving auroras on planets far from Earth. Even airless bodies feel it, because charged particles interact with surfaces and exospheres. The wind carries not only particles, but also magnetic structure, sectors, waves, and discontinuities that sweep past like rotating weather fronts. The sun's rotation imprints a repeating pattern, yet eruptions can break the rhythm. The planets orbit inside a flow that never truly stops. Even in calm periods, the wind carries shocks, discontinuities, and rotating structures, and each carries information about the sun's surface. A coronal hole can produce a high-speed stream that catches slower wind ahead, piling up into a compression region. A coronal mass ejection can drive a shock that propagates outward for weeks. These traveling disturbances are the storms of interplanetary space. They are measured in magnetic field strength, particle flux, and plasma speed. As distance grows, sunlight weakens and travel times stretch. The idea of an edge becomes less about sight and more about instruments, because the outer solar system is dim and vast. Light intensity drops with the square of distance, so at 10 times Earth's distance, the sun is 100 times fainter. Cameras see less, but sensors still feel the wind and fields. In deep space, a plot of particle counts can be more revealing than any photograph. The frontier becomes a set of graphs that change character. Beyond the outer planets lies the Kuiper Belt. It is a broad ring of icy bodies and dwarf planets that preserves early solar system material, cold enough to keep ancient ices stable. These objects are leftovers from planet formation, fragments that never became a planet. Their surfaces can be darkened by radiation and micrometeoroid impacts, yet they hold clues to primordial chemistry. In wide visualizations, the belt is not a neat ring, but a thick, flattened swarm. It is a region, not a line. We infer its structure from surveys and from the orbits of objects we can track. Their clustering and inclinations reveal a population, not a boundary, and the statistics become a map. Each new detection adds a point to a phase space portrait: distance, tilt, eccentricity, and resonance. Some objects are trapped in orbital resonances with Neptune, repeating gravitational rhythms that keep them stable. Others wander more freely, hinting at a history of migration and scattering. The belt's shape is a fossil record written in motion. Farther out is the scattered disk. Its objects have elongated, tilted orbits shaped by past encounters with Neptune, and long-term resonances that can pump eccentricity over millions of years. They spend most of their time far from the sun, then swing inward briefly, like deep-sea creatures surfacing for a moment. Their paths tell of gravitational nudges that accumulated into dramatic changes. This is not a tidy frontier, it is a ragged transition zone. The solar system's architecture blurs as you approach its outskirts. These bodies show that the solar system has a ragged boundary. Gravity does not end cleanly, and orbital histories remain written in trajectories, sometimes for billions of years. A single close encounter can rewrite an orbit, but so can a long, slow resonance that acts like a metronome. When we talk about the edge, we are really describing where stable patterns become rare. The outer solar system is a museum of dynamical processes. Its exhibits are moving, not stationary. Some comets arrive from much farther than the Kuiper Belt. Their long periods and near isotropic approach directions imply a distant reservoir, one that surrounds the solar system rather than lying in a flat disk. They arrive from above and below the planetary plane, as if the sky itself were a source. Their orbits are often barely bound, with energies that suggest a gentle push could send them away forever. Each comet is a messenger, but also a clue about where it slept. The distribution of their arrival directions is the key. That reservoir is the hypothesized Oort cloud. We cannot image it directly, yet comet orbits act like test particles mapping an unseen swarm, and the swarm must be enormous to explain what we observe. The idea traces back to Jan Oort in the mid-20th century, when patterns in long-period comet orbits demanded an explanation. If comets came only from the planetary region, their orbits would not look so isotropic. A distant, roughly spherical cloud solves the puzzle. It turns a statistical pattern into a physical place. In visual terms, the Oort cloud is a halo of deep freeze debris. Imagine a faint, distant shell of icy bodies, so far away that the sun is just another bright star. The distances are so large that a single orbit can take millions of years. At that scale, the solar system is already interacting with the galaxy's tides and passing stars. A subtle gravitational nudge can change a comet's perihelion and send it inward. The cloud is not just storage. It is a slow exchange between star and galaxy. This is a second lesson about edges. We often detect boundaries by their effects, not by direct pictures, and inference becomes a form of exploration. The edge is not always a visible cliff. Sometimes it is a change in probability. We look at what arrives, how often it arrives, and from which directions. Then we work backward to the structure that must exist. In deep space, absence of imagery does not mean absence of knowledge. Even the Oort cloud is still part of the sun's gravitational reach. But gravity is not the only influence that defines a frontier, and that is where the story turns. The sun also creates an electromagnetic territory, and electromagnetism can dominate where matter is ionized. Charged particles respond to fields instantly compared with the slow pull of gravity. The solar wind carries those fields outward, expanding the sun's influence like a bubble. The question becomes, where does that bubble end? The sun also creates an electromagnetic territory. The solar wind inflates a vast bubble in the surrounding interstellar medium, pushing against the galaxy's thin gas and magnetic field. This bubble is not static. It breathes with the solar cycle, expanding and contracting as solar activity rises and falls. It is also asymmetric because the sun moves through the local interstellar medium. Motion adds a headwind, and the headwind reshapes the bubble. Even a gentle drift through the galaxy can sculpt a boundary. That bubble is the heliosphere. It is a moving cavity of solar plasma and magnetic field that surrounds the planets and extends far beyond them, a kind of stellar magnetized atmosphere. The heliosphere is also a filter, modulating which high-energy particles can enter the inner solar system. It deflects some charged cosmic rays, while letting others through depending on energy and magnetic conditions. In this way, it influences radiation exposure for spacecraft and, indirectly, for life. A bubble can be protective without being perfect. The heliosphere is not a perfect sphere. It is shaped by the sun's motion through the galaxy and by the pressure of interstellar gas and fields which push back from the outside. The interstellar magnetic field can drape over the heliosphere, bending and compressing it. Neutral atoms from interstellar space can also slip inside because they are not guided by magnetic fields until they become ionized. Once ionized, they are picked up by the solar wind and accelerated, becoming pickup ions. Those pickup ions change the wind's energy budget, subtly altering the bubble's dynamics. Inside it, the solar wind begins supersonic. It streams outward, faster than pressure waves can travel back toward the sun, which means the sun cannot easily hear the conditions far away. The wind carries a mix of protons, electrons, and a smaller fraction of heavier ions. It also carries turbulence, magnetic fluctuations that scatter particles and transport energy. As it expands, it cools and becomes more tenuous. Yet it remains a coherent flow for billions of kilometers. Eventually, the wind slows. At the termination shock, the solar wind drops from supersonic to subsonic speeds as it begins to pile up, like traffic compressing near a narrowing lane. This happens because the outward pressure of the wind weakens with distance, while the external pressure from interstellar space becomes comparatively important. The termination shock is a consequence of competing environments. It marks where the wind can no longer expand freely. Beyond it, the flow is still outward, but it is slowed and heated. This shock is not a wall. It is a transition where kinetic energy is converted into heat, turbulence, and energetic particles, and the conversion is messy. Some particles are reflected and accelerated, gaining energy through repeated interactions with moving magnetic irregularities. These energetic particles can propagate both inward and outward, becoming a radiation hazard and a diagnostic signal. The shock's location can shift with solar conditions, moving inward during periods of weaker solar wind. It is an edge that breathes. Beyond the termination shock lies the heliosheath. It is a thick region of slowed, heated solar wind that churns as it meets resistance, and it is more complicated than early models suggested. Magnetic fields there can be compressed and tangled, and plasma flows can be diverted sideways. The heliosheath is a mixing zone where solar material and interstellar influences begin to negotiate. If the termination shock is a sudden transition, the heliosheath is a long argument. It is where the bubble's interior learns about the outside. At the outer limit sits the heliopause. It is the pressure balance boundary where solar influence yields to the local interstellar medium, and the definition is physical rather than poetic. On one side, the solar wind's plasma and magnetic field dominate. On the other, interstellar plasma and magnetic pressure dominate, along with the ram pressure of the sun's motion through the local cloud. The heliopause is not where gravity ends, but where the solar wind's authority does. It is the first boundary that feels like a true frontier. The heliopause is an edge with a definition. It is where outward solar wind pressure matches the inward pressure of interstellar plasma and magnetic fields, and that match can be tested. Pressure here includes particle pressure, magnetic pressure, and dynamic pressure from bulk motion. Because multiple pressures contribute, the boundary can shift when any of them changes. A stronger solar wind can push the heliopause outward. A denser interstellar region could squeeze it inward. Yet even here, the edge is not a sharp membrane. It can ripple, shift with the solar cycle, and allow some particles to leak across depending on energy and charge. Magnetic reconnection can open pathways where field lines from different domains connect. Neutral atoms can cross freely because they ignore magnetic fields until ionized. Energetic particles can also diffuse across, blurring the boundary in a way that depends on turbulence. The heliopause is a frontier, but it is not a fence. To understand how we know this, we follow two spacecraft built for another era. Voyager 1 and Voyager 2 become our guides to a real frontier, not because they were designed for it, but because they endured. They launched in 1977 to tour the giant planets, at a time when computers were slow and memory was precious. Their gold records carried messages for any distant finder, but their real message has been data. Decades later, those data would define an edge no human could approach. They launched in 1977 to tour the giant planets. Their gravity assists turned them into long-duration probes of the outer solar system. using planetary motion as a kind of celestial slingshot. The mission took advantage of a rare alignment of the outer planets, a window that appears only every 176 years. Jupiter and Saturn provided the first boosts, while Uranus and Neptune became targets for Voyager 2. The spacecraft were not just traveling, they were being guided by gravity's geometry. Each flyby was both a scientific triumph and a navigational gamble. Voyager carries magnetometers, plasma instruments, and particle detectors. These tools measure fields and charged particles rather than taking scenic images, because the frontier is defined by invisible quantities. Magnetometers track the strength and direction of magnetic fields, revealing waves, turbulence, and large-scale structure. Plasma instruments measure density, temperature, and flow speed, turning a sparse environment into a readable signal. Particle detectors count energetic ions and electrons across different energies. Together, they translate emptiness into numbers with meaning. In 2004, Voyager 1 crossed the termination shock. It detected a change in the solar wind's speed and an increase in energetic particles, consistent with a shock that accelerates and heats. The crossing was not a single clean step, because the shock itself can move. Voyager 1 encountered it, then saw conditions fluctuate, suggesting a boundary that wobbled. This was our first in situ contact with the solar wind's slowing point. A theoretical feature became a measured place. In 2007, Voyager 2 crossed the termination shock as well. Its instruments confirmed that the shock is irregular and varies with direction and time, and that the heliosphere is asymmetric. Voyager 2 crossed at a different distance than Voyager 1, hinting that the termination shock is closer in some directions. That difference is a clue about external pressure and magnetic shaping. Two spacecraft, separated in space, turned one crossing into a three-dimensional insight. The frontier had contours. The heliosheath was not quiet. Voyager data showed turbulent magnetic fields and complex particle populations that did not match simple textbook pictures. And the mismatch became the point. Models had imagined smoother flows, but reality offered fluctuations and unexpected distributions. Energetic particles were abundant in ways that suggested additional acceleration processes. Magnetic field strength varied, and the direction sometimes wandered. The heliosheath was not a calm moat. It was active, noisy, and evolving. Then came the question that sounds simple, but is not. How do you know you have crossed into interstellar space when the view outside the window does not change? You do not see a sign, and you do not hear a sound. The only evidence is in the instrument's steady, persistent shift. So the problem becomes one of criteria and confirmation. What must change, and how long must it remain changed? You do not see a sign. You watch for coordinated changes in multiple measurements, and you test whether they persist. Because single instruments can mislead, a sensor can fail, or a transient event can imitate a boundary. Scientists look for a pattern across independent channels, like a doctor comparing vital signs. They also look for stability, because a true crossing should not reverse after a day. The edge is a state change, not a moment of drama. One key signal is plasma density. Interstellar plasma is generally denser than the tenuous solar wind in the outer heliosphere, even though both are extremely thin by Earth standards. Density here is measured in particles per cubic centimeter, numbers so small they challenge intuition. Yet the difference matters, because it changes how waves propagate and how particles interact. A denser plasma supports different oscillation frequencies. Those frequencies can be detected as plasma waves. Voyager 1 could not directly measure plasma with its main instrument, which had failed earlier. It used plasma wave observations triggered by solar eruptions, which sent shocks outward like distant thunder. When those shocks passed Voyager, they excited oscillations in the surrounding plasma. The frequency of those oscillations depends on electron density. By measuring the frequency, scientists inferred the density indirectly. Even a broken instrument did not end the measurement. It changed the method. Those waves revealed a higher density consistent with interstellar space. The density increase was a fingerprint of a new medium because it persisted and matched expectations for the local interstellar environment. It was not just a spike, it was a new baseline. The data suggested Voyager 1 was no longer in the solar winds domain. The spacecraft had entered a region where the galaxy's plasma set the rules. The frontier announced itself as a different kind of background. Another key signal is particle behavior. Inside the heliosphere, energetic particles from the Sun and the Helios heath are common, and their flux reflects solar activity and shock acceleration. Outside, galactic cosmic rays become more prominent because the heliosphere's shielding weakens beyond the boundary. A sustained drop in heliospheric particles paired with a rise in cosmic rays indicates a crossing. This is like stepping out of a sheltered courtyard into a wider, harsher wind. The particle environment becomes more galactic than solar. Magnetic fields complicate the story. Scientists expected a sharp change in field direction at the heliopause, yet Voyager 1 saw a similar direction continue, and that continuity sparked debate. If the interstellar magnetic field drapes over the heliopause, it can align with the heliospheric field near the boundary. That draping can make the direction change subtle, even when the environment has changed. It is a reminder that boundaries can be layered rather than abrupt. The magnetic signature may be a gradient, not a switch. That forced a more careful interpretation. The boundary could be layered, or magnetic fields could drape and align, masking a simple directional switch. And so, scientists leaned on multiple lines of evidence. They compared particle populations, wave-derived densities, and long-term trends. They asked whether the changes were consistent with a temporary event or a permanent transition. The process was cautious because declaring interstellar space is a claim with weight. In science, an edge is not proclaimed, it is demonstrated. In 2012, Voyager 1 observed the combined signatures that held steady. Plasma density rose, heliospheric particles fell, and cosmic rays increased, and the pattern persisted. That persistence mattered more than any single reading, because it suggested a stable new environment. The spacecraft had crossed a boundary that did not drift back over it. The heliopause in that direction had been passed. The first human-made object had entered interstellar space by measurable criteria. That persistence mattered more than any single reading. An edge in space is confirmed by repeatable states, not by one dramatic moment, and repeatability is the difference between noise and knowledge. The Voyagers did not deliver a cinematic cut. They delivered a statistical certainty. The crossing was a change in distributions, not a flash of light. It was the quiet kind of discovery that only instruments can announce. And yet it reshaped our mental map. In 2018, Voyager 2 crossed the heliopause with working plasma instruments. It measured the density jump directly and strengthened the case with independent data, providing a second confirmation. Voyager 2 also saw changes in particle populations consistent with leaving the heliosphere. Two crossings in different directions showed the heliopause is not at one fixed distance. The bubble is asymmetric, and the galaxy presses unevenly. The edge has shape. Together, the Voyagers show how science detects a frontier. You define what should change across a boundary, then you measure until the pattern is undeniable, and you remain open to surprises. The method is disciplined, but it is also imaginative, because you must decide what counts as a signature. The Voyagers also show the value of longevity. A spacecraft that survives for decades can watch slow transitions that short missions would miss. Time here is part of the instrument. The heliopause is also a metaphor with teeth. Each time we name an edge, we discover it is embedded in a larger enclosure, and the enclosure has its own rules. Earth's atmosphere sits inside Earth's magnetosphere. Earth's magnetosphere sits inside the heliosphere, and the heliosphere sits inside the galaxy. The nesting is not just conceptual, it is physical and measurable. Each layer filters what comes next. Earth's atmosphere sits inside Earth's magnetosphere. Earth's magnetosphere sits inside the heliosphere, and the heliosphere sits inside the galaxy, like a set of translucent shells. From the ground, the sky feels like the boundary. From orbit, the magnetosphere becomes the boundary. From the outer solar system, the heliopause becomes the boundary. Each perspective changes what outside means. The edge is always relative to what you can measure. The local interstellar medium is the next environment. It is not empty space, but a thin mixture of gas, dust, magnetic fields, and high-energy radiation. And it has its own weather. Its density is low, yet over vast distances, it contains significant mass. Its temperature can be warm compared with molecular clouds, and its ionization state can vary. Magnetic fields thread through it, influencing how charged particles move. In interstellar space, the background is active, not inert. Its gas is mostly hydrogen and helium with trace, heavier elements. Much of it is ionized plasma, threaded by magnetic fields that guide particle motion, even when the fields are weak. Ionized gas responds to electromagnetic forces, which can dominate over collisions in such thin conditions. That means particles can travel long distances before hitting anything. The medium behaves less like air and more like a collisionless fluid. Yet collective effects, waves and instabilities still arise. Dust grains drift through it and interact with light and fields. They carry charge, seed chemistry, and contribute to the opacity of the galaxy, even though each grain is microscopic. Dust can absorb starlight and re-emit it in infrared, changing how the galaxy looks across wavelengths. Grains can also act as surfaces where molecules form, including molecular hydrogen. In a sense, dust is a chemical workshop floating in space. It is small-scale matter with large-scale consequences. Cosmic rays move through this medium like a penetrating fog. They are accelerated by supernova remnants and other energetic processes across the Milky Way, and they carry energies far beyond what human technology typically produces. When cosmic rays strike matter, they can ionize atoms and trigger cascades of secondary particles. They also carry information about distant astrophysical accelerators. Their paths are bent by magnetic fields, making their origins difficult to trace. Even so, their intensity tells us about the shielding effect of bubbles like the heliosphere. The interstellar medium has structure. It has clouds, cavities, shocks, and turbulence. And the Sun currently travels through a local cloud of relatively warm gas. That local environment is not representative of the entire galaxy, because the interstellar medium is patchy. Some regions are dense and cold, others hot and tenuous. Past supernovae can carve cavities, leaving hot bubbles that persist for long periods. The Sun's neighborhood is a particular chapter in a larger, changing galactic story. Calling it a thin ocean is not poetry alone. Like an ocean, it has currents and waves, and it transmits pressure and magnetic disturbances, though the water is plasma and gas. Magnetohydrodynamic waves can travel through it, carrying energy and information. Turbulence can cascade from large scales to small, shaping how particles diffuse. In this ocean, the concept of a current is tied to both motion and electric charge. The analogy holds, as long as we remember the medium is collisionless and magnetized. The heliosphere is carved by that ocean's pressure. Its size changes as the sun's wind strengthens or weakens, and as interstellar conditions vary, and those variations can unfold over years or longer. The solar cycle modulates the wind and the heliospheric magnetic field, altering how cosmic rays penetrate. Interstellar density and magnetic pressure can also change as the sun moves through the galaxy. The heliosphere is not a permanent bubble of fixed radius. It is a dynamic interface between star and galaxy. This is why the heliopause is not a permanent border. It is a living boundary that responds to cycles, motion, and the surrounding galactic environment. And it can shift without warning to our intuition. If the sun's wind pressure drops, the heliopause can retreat. If a stronger interstellar flow presses in, it can be compressed. Even the boundary's fine structure can change, with ripples and instabilities. The frontier is alive because both sides are alive. The word universe starts to feel different here. The solar system is not the universe, yet it is our first laboratory for how the universe organizes space and for how it hides structure in the invisible. We learn that emptiness is a medium and that medium has properties. We learn that boundaries are defined by competing pressures and fields. We learn that instruments, not eyes, are the primary sense organs of deep space exploration. And we learn that scale changes meaning. Scale becomes a recurring reveal. A planet's sky gives way to a star's bubble, and that bubble becomes a small pocket inside a galaxy. And the galaxy is only one among countless others. The mind resists these steps, because each step shrinks what felt central. Yet the physics remains continuous, with the same forces appearing in different balances. Magnetic fields matter here, gravity dominates there, radiation shapes another region. The universe is not one environment, it is a mosaic of regimes. The Milky Way is a disk of stars, gas, and dust embedded in a much larger halo. Our Sun is one star among hundreds of billions, orbiting the galactic center on timescales that dwarf human history. The disk has spiral structure shaped by gravity and motion, and it contains much of the star-forming material. Above and below the disk lies a halo of older stars and dark matter, extending far beyond the visible. From that perspective, the heliosphere is almost microscopic, yet for us, it is the first boundary we can touch. From this distance, the heliosphere is a local weather system. It is a protective cocoon that modulates cosmic rays and filters interstellar particles, reducing radiation levels in the inner solar system. The modulation depends on particle energy, because high-energy cosmic rays penetrate more easily. It also depends on the heliospheric magnetic field's polarity and structure, which change over the solar cycle. The bubble is a shield with pores. It is protection, but not immunity. Even its protection is partial. Some cosmic rays penetrate, and some interstellar neutrals drift in, become ionized, and are swept outward as pickup ions, altering the plasma's composition. Those pickup ions can be further accelerated to become anomalous cosmic rays, a population linked to heliospheric boundaries. This chain shows how the heliosphere is not isolated. Matter crosses, changes identity, and crosses again. The boundary is an engine for transformation. The boundary teaches another lesson about knowledge. We do not need to touch an edge to map it, but we must know what to measure, and measurement requires theory. Theory tells us which variables should change at a boundary. Instruments tell us whether they do. When the data disagree, theory must adapt, and instruments must be reinterpreted. The heliopause is a case study in that dance. It is where abstract models met stubborn reality. Voyager's measurements also reveal humility. The heliosphere's shape, its shocks, and its magnetic behavior are still being revised as data accumulates, and as new models incorporate complexity. The voyagers sampled only 2 paths through a vast, 3-dimensional structure. They did not give us a full map, but they gave us anchor points. Those points constrain what is possible. They also remind us how much remains unknown. This chapter anchors mystery in evidence. We can name real thresholds, tie them to instruments, and show how a boundary becomes a scientific claim, not a feeling. The mystery is not diminished by measurement. Instead, measurement sharpens the questions. What is the heliosphere's true shape, and how does it respond to changing interstellar conditions? How porous is the heliopause, and how does reconnection behave there? Each answer opens a more precise unknown. Yet the central question keeps widening. When we ask what lies beyond the edge of space, we are also asking what counts as an edge at all, and whether edges are ever final. Beyond the heliopause is not a void. It is another medium with its own pressures and fields, and it is only the first layer of interstellar reality. The frontier is not a finish line, it is a handoff between governing influences. Beyond that medium lies the architecture of the galaxy. Gravity becomes the dominant designer, shaping orbits, spiral structure, and the distribution of matter, while magnetic fields and feedback shape the details. Stars move in a collective potential, and gas responds by forming waves and arms. Over long timescales, galaxies evolve through mergers, accretion, and internal dynamics. The heliosphere is a local feature within that grand structure. It is a bubble floating in a city of stars. If our sun has an edge, does the Milky Way have one? We move from a stellar neighborhood to a galactic city, where the next frontier is mass, and mass is often unseen. The galaxy's visible disk fades into a halo, and the halo hints at dark matter's gravitational scaffolding. Where does the galaxy's influence truly yield to intergalactic space? What defines that boundary? Density, gravity, or something else? The question echoes the heliopause question, but at a larger scale. The sky does not end. It changes jurisdiction, from air to magnetism to wind, and from wind to the galaxy's wider sea, and each jurisdiction has its own laws. The edge keeps moving as we learn to see farther and as we learn which measurements matter. What feels like an ending becomes a threshold. What looks like emptiness becomes a medium. That is the pattern that will carry us into the deeper, stranger horizons ahead. If our sun has an edge, does the Milky Way have one? Something like a shoreline where the familiar finally stops. We leave the heliopause behind and enter a larger jurisdiction where gravity sets the weather and time sets the pace. Out here, the medium is thinner and colder, yet the rules feel heavier, because mass, not atmosphere, decides what happens next. From inside the disk, the galaxy looks like a band of light stretched across the night. It glows unevenly, bright in places and torn by dark lanes that look like missing paint. That band is not a picture of the whole Milky Way, because we are embedded in it. Distance, dust, and perspective turn a 3-dimensional system into a misleading skyline, an inside view of a city where you can't step back. Even the word Milky Way carries history, because ancient observers named what they could not resolve. To the naked eye, it was a pale river, a spill of light across blackness. Only after telescopes did it fracture into countless stars, and only much later did we learn it was a disk seen from within. The first lesson of the rim is humility. Our viewpoint shapes the story before the story even begins. Start with what we can map in starlight, because stars are the easiest tracers to see. The Milky Way has a thin rotating disk where most bright stars and gas reside. The disk is not a flat record. It is a dynamic sheet, shearing as different radii orbit at different speeds. At the center sits a dense bulge of older stars around the supermassive black hole. That black hole, Sagittarius Aegis, is quiet by quasar standards, yet its gravity anchors the innermost architecture. Spiral arms thread the disk as patterns of enhanced density, not rigid structures. They are closer to traffic jams than to permanent walls. Regions where gas piles up, compresses, and triggers star formation. In those crowded lanes, massive blue stars burn fast and die young, lighting the arms like brief flares. When those stars explode as supernovae, they seed the gas with heavier elements, enriching the next generation. The disk is not uniform, and it never was. It has a thin component rich in young stars and molecular clouds, where the raw material for planets stays cold enough to clump. It has a thicker component with older stars on puffed-up orbits, stirred by ancient encounters and long-term gravitational heating. The thick disk is a memory of earlier eras, when the galaxy was rougher, more chaotic, and still assembling. The disk also warps and flares at large radius, showing that equilibrium is imperfect. From far above, the outer disk would look slightly bent, like a vinyl record left too close to heat. Part of that warp may come from the pull of satellite galaxies, and part from the way infalling gas arrives with misaligned angular momentum. A galaxy is not a sealed machine. It is an open system exchanging matter and momentum. Above and beyond the disk lies the stellar halo, and the word halo can mislead. It is not a glowing ring, but a sparse population of old stars spread through an enormous volume. These stars move on eccentric, tilted orbits that ignore the disk's tidy rotation. Many are metal-poor, meaning they formed early, before repeated cycles of star formation enriched the gas. Their chemistry is a kind of time stamp, an elemental signature of the young universe. Globular clusters orbit there as compact relics of early star formation. Each cluster holds hundreds of thousands of stars in a sphere only a few dozen light-years across. They are ancient, often more than 10 billion years old, and they survive because their self-gravity is strong. Some may be the stripped nuclei of former dwarf galaxies, left behind after the rest was torn away. The halo is faint, but it carries the memory of past mergers, written not in words, but in trajectories. Gas adds another layer, and it behaves differently because it can collide, cool, and shock. Atomic hydrogen extends beyond most visible starlight in a thicker, more diffuse disk. It is detected through a particular radio whisper, the 21-centimeter line, produced by a rare flip in hydrogen's electron-proton spin alignment. Hot ionized gas forms a corona that reaches far into the halo, heated to millions of degrees by gravitational infall and supernova feedback. These gas phases matter because they trace gravity where stars are scarce, and because they regulate future star formation. Dust is the first reason the Milky Way's structure is hard to see. Dust grains are tiny, often comparable in size to the wavelengths of visible light. So they absorb and scatter optical photons efficiently. Along the crowded plane, those grains build up into dark rifts that look like emptiness. Yet the darkness is not a void, it is a veil, and behind it, the disk continues. In visible light, our own galaxy hides itself with the debris of its own star-making. Dust also reddens what it does not fully block, shifting starlight toward longer wavelengths. That effect, called extinction and reddening, complicates distance estimates because stars appear dimmer and cooler than they truly are. Astronomers correct for it with models and multi-band observations, but the correction is never perfect. The rim is not only far away, it is also filtered through intervening material. When we map the galaxy, we are always mapping through something. To see through dust, we change the wavelength, and the shift feels like switching senses. Infrared light penetrates dust better and reveals embedded stars and warm dust emission. In infrared surveys, star-forming regions appear as glowing knots, and the bulge becomes clearer as a dense swarm of older stars. Radio observations, especially the 21-centimeter line of neutral hydrogen, map gas across the disk and beyond. The radio sky is not a photograph. It is a set of measurements translated into images, a reminder that seeing in astronomy often means decoding. Those maps reveal that the Milky Way is not a clean spiral sketch. Arms are patchy and overlapping along our sightlines, and the geometry is unforgiving from our position inside the disk. Distances are often inferred from motion, which depends on a model of rotation. In the inner galaxy, the same observed velocity can correspond to two different distances along the line of sight. Even the basic question of where an arm begins can be a problem of geometry, like trying to draw a coastline while standing in the surf. Historically, the problem of our galaxy's structure took centuries to sharpen. Early star counts hinted at a flattened system, but dust fooled those counts by hiding distant stars. Radio astronomy in the 20th century changed the game, because hydrogen does not care about optical darkness. Later, infrared surveys filled in what radio could not, revealing the stellar backbone beneath the dust lanes. Each new window made the Milky Way look larger, more complex, and less like a textbook diagram. Now the documentary pivots from travelogue to cosmology. A galaxy is not just a collection of stars. It is a gravitational ecosystem embedded in a larger, mostly invisible halo. The visible parts are the bright, busy surface, while the deeper mass sets the rules. If we want an edge, we must decide what we mean by galaxy in the first place. So what is the Milky Way's edge? The answer depends on which component you choose and which measurement you trust. Edges in astronomy are rarely walls. They are thresholds where densities fall and influences compete. The rim is less like a fence and more like a gradient, one that changes depending on what you measure. One edge is photometric, and it begins with a practical limit: detection. It is where the surface brightness of the stellar disk drops below what our instruments can reliably separate from the background. That boundary moves outward as surveys improve, and as we stack faint light from many exposures. A deeper camera makes the galaxy larger without changing the galaxy. The rim, in this sense, is partly a property of our patience and technology. Another edge is structural, and it is written in stellar populations. It is where the thin disk gives way to the thick disk, and then to the stellar halo. That transition is gradual and asymmetric, because the disk is warped and the halo is lumpy. In one direction, you may hit the halo sooner, while in another, the disk's flare keeps stars present farther out. The galaxy's shape depends on where you stand and which stars you count. Another edge is gaseous, and it is tied to the physics of cooling and shielding. It is where cold gas becomes scarce enough that star formation shuts down. Molecular clouds require pressure, shielding from ultraviolet radiation, and metals that help gas radiate away heat. All of those conditions decline with radius, so the outer disk becomes a place where gas stays more diffuse and less willing to collapse. The star-forming disk ends before gravity ends, and that mismatch is one of the rim's key clues. Another edge is dynamical, and it is the most consequential one. It is where the Milky Way's gravitational pull stops dominating and the local group environment takes over. That boundary is not defined by light, and it is not visible as a line in the sky. It is defined by competing gravitational potentials, by the balance between being bound to the Milky Way and being part of a larger shared system. In that sense, the rim is an argument between neighbors. To understand the dynamical edge, we need the galaxy's mass profile. Mass determines orbital speeds at different radii and orbital speeds are measurable. If we can measure how fast stars and gas orbit, we can infer how mass is distributed. This is the same logic that lets us weigh the sun by watching planets. But the galaxy is messier. We are inside it, and our measuring sticks are imperfect. This is where rotation curves enter, and the concept is deceptively simple. For an object in a roughly circular orbit, the required speed depends on how much mass lies inside that orbit. In a simple picture, orbital speed should fall with distance once most mass is inside the orbit. That is how planets behave around the Sun, because the Sun holds most of the mass. Many expected galaxies to behave the same way, with outer stars slowing down like distant planets. But the Milky Way and other spirals do not. Beyond the bright inner regions, orbital speeds stay high instead of dropping quickly. The curve is flatter than visible matter predicts, and it stays stubbornly flat across large radii. The outer galaxy moves as if extra mass is present, mass that does not shine. The rim, when defined by gravity, stretches far beyond the rim defined by starlight. The measurement is not one technique, and that redundancy is part of its power. We use Doppler shifts of gas in the disk, where spectral lines slide in frequency as gas approaches or recedes. We use proper motions of masers, natural microwave lasers in star-forming regions, which can be tracked with exquisite precision. We use the motions of stars, including halo stars that plunge through the disk on long orbits. We combine these with distance estimates that carry their own uncertainties, yet the broad result persists across methods and across galaxies. Even the idea of circular speed is an approximation, because real orbits are perturbed by bars, spiral structure, and past interactions. The Milky Way has a central bar that can drive non-circular motions in the inner disk. Gas clouds can stream along arms, and stars can migrate radially over billions of years. Yet when we average over the chaos, the large-scale gravitational requirement remains. Something massive is shaping the motion, even where the light thins. The inference is simple and unsettling. If gravity is normal, then there must be more mass than we can see. The missing mass is not a small correction, and it is not confined to a hidden pocket. It dominates the galaxy's mass budget, outweighing the luminous stars and gas by a wide margin. The Milky Way, in this accounting, is more invisible than visible. Use an analogy that stays honest, because the concept is easy to distort. Imagine a city at night where only streetlights are visible. The streetlights mark where people are, but they do not show the roads and bridges. You can still infer the infrastructure by watching traffic flow, because cars follow constraints you cannot see. Gravity is the traffic pattern, and the unseen infrastructure is the scaffold shaping motion. That scaffold is what we call dark matter, and the name is both descriptive and incomplete. It does not emit, absorb, or reflect light in the usual ways, so it does not make images the way stars do. We detect it through gravitational effects on visible matter and on light passing through space. It is the first major something stranger beyond the visible, because it forces us to accept a dominant component we cannot directly photograph. Dark matter is not a patch added at the rim, and it is not a fog sprinkled between stars. It forms a halo that envelops the luminous disk and bulge, extending far beyond the region where most stars live. In many models, the visible galaxy is a bright core inside a much larger dark structure. If you could see mass the way you see light, the Milky Way would look like a small lantern embedded in a vast, dim sphere. The Milky Way's dark halo is inferred in several ways, and each method probes a different scale. Satellite galaxies orbit the Milky Way at large distances, and their speeds require a deep gravitational potential. Some satellites move fast enough that, without a massive halo, they would not remain bound. Stellar streams from disrupted satellites trace the shape of that potential over long arcs, because their stars remember the orbit they were torn from. The hot gas corona also responds to the same gravity, because without confinement, it would escape into intergalactic space. Gravitational lensing adds a more general line of evidence, and it is one of the most elegant. Massive halos bend background light, distorting galaxy shapes in subtle, measurable patterns. In strong cases, lensing makes arcs and rings, but more often it is weak and statistical. For the Milky Way, lensing is harder to use directly because we are inside the lens. Across the universe, it confirms that halos are real and common, and that the same invisible mass appears wherever we look. Cosmic structure formation ties the story together because it turns a galactic mystery into a universal one. The early universe had tiny density fluctuations imprinted in the cosmic microwave background. Dark matter, if it is cold and weakly interacting, clumps early and builds a scaffold of potential wells. Gas falls into those wells, heats in shocks, cools by radiation, and forms stars. Galaxies become visible traces of an invisible framework, like frost outlining the branches of a tree you can't otherwise see. This changes how we define a galactic rim, because the galaxy is no longer just its stars. The luminous disk may end at a few tens of kiloparsecs, depending on how you define its faint outskirts. The stellar halo reaches farther, but remains sparse, and its density falls with radius. The dark matter halo can extend hundreds of kiloparsecs, blending into the local group's shared environment. The rim becomes a layered boundary, with different answers depending on whether you follow light, gas, or gravity. Even that halo edge is not sharp, and the fuzziness is partly conceptual. In simulations, halos have a virial radius defined by an overdensity threshold, which is a convention tied to cosmology. It marks a region that is roughly in dynamical equilibrium, not a physical shell. Material can orbit beyond that radius and still be bound, especially on elongated trajectories. The boundary depends on how you choose to define equilibrium and on what timescale you consider settled. The Milky Way's rim is also shaped by interaction, because galaxies grow by taking. The galaxy is not isolated, and it never was. It grows by accretion, by stripping smaller systems and by merging with them. These processes are not just ancient history. They are ongoing, slow-motion events. The edge is where these processes are easiest to see, because the outskirts are less mixed and less crowded. Tidal streams are the clearest signatures, and they are hauntingly beautiful in wide field maps. When a dwarf galaxy or globular cluster is pulled apart, its stars spread along its orbit. Over time, those stars form long, thin streams that wrap around the Milky Way like faint ribbons. They are not decoration, and they are not random. They are dynamical evidence of ongoing assembly, and they act like test particles tracing the gravitational field. The Sagittarius dwarf galaxy is a key example, and it is a lesson in slow destruction. It is being disrupted and contributes stars to the halo, leaving multiple wraps of debris around the sky. Its stream crosses the galactic plane and loops through the halo, sometimes passing relatively near the Sun. That debris helps map the Milky Way's gravitational field and the halo's shape. Each wrap of the stream is a constraint on the unseen mass distribution, because the orbit depends on the potential. The Magellanic Clouds add another interaction, and they change the mood from faint to obvious. They are massive satellites with their own gas and star formation, visible as bright patches in the southern sky. Their motion perturbs the Milky Way's outer disk and halo, stirring ripples that can be traced in stellar motions. Their associated gas stream, stretching across the sky, shows that the Milky Way is exchanging material with its companions. The rim is not a boundary of ownership. It is a zone of exchange. Dwarf galaxies orbit in a population, and their diversity hints at the complexity of the halo. Some are bright enough to detect easily, with clear stellar populations and measurable internal motions. Many are ultra-faint and were found only with deep surveys, where a handful of stars move together against the background. Their abundance and distribution test dark matter models, because halos should host subhalos in large numbers. Each dwarf is a laboratory where dark matter's gravitational dominance is extreme. This leads to a tension inside the dark matter story, and it sits right at the rim. Simulations predict many small subhalos, far more than the number of luminous dwarfs we easily observe. Observations find fewer luminous dwarfs, implying that many subhalos may be dark, unable to form stars efficiently. Reionization, supernova feedback, and tidal stripping can all suppress visible growth in small halos. That possibility makes the galaxy's outskirts feel crowded with invisible structure, as if the rim is populated by ghosts. Edges become messy because gravity makes long memories, and the halo preserves them. A merger from billions of years ago can leave phase space scars that persist, even after the stars are spatially mixed. Those scars appear as coherent motions, clumps in velocity space, and streams that are faint but organized. The halo is a fossil record written in orbits, not in monuments. To read it, we need precise motions and distances, and we need to accept that the past is still moving. Gaia changes what is possible, and its impact is hard to overstate. By measuring positions and proper motions for over 1 billion stars, it turns the Milky Way into a dynamical data set. It reveals streams, moving groups, and halo substructure that were previously invisible in the noise. It refines the rotation curve and the mass distribution by anchoring distances and motions with unprecedented consistency. In Gaia's maps, the galaxy feels less like a picture and more like a living system. Yet even with Gaia, the rim remains partly inferred, because the outskirts resist easy measurement. The farthest halo stars are rare and faint, and many are beyond precise parallax reach. Distance errors grow with range, and selection effects shape what we detect, because we only see certain kinds of stars at great distances. The galaxy's true extent is not a single number. It is a set of confidence intervals, and those intervals widen as we approach the edge. Now widen the scale again without changing the question. If galaxies have halos, then halos live in a larger environment. The Milky Way is one node in the local group, and the local group is one knot in a cosmic network. The rim becomes less about a single galaxy and more about the structure it inhabits. What looks like an edge from one scale becomes a bridge at the next. The cosmic web is the next structure beyond the galactic rim, and it is both real and difficult to visualize. Matter in the universe is not spread evenly. It forms filaments, sheets, and knots where galaxies cluster, and those structures span tens to hundreds of millions of light years. Between them lie voids, vast regions of low density that still contain some matter. The universe is not a smooth ocean, it is a textured landscape. The web is inferred from galaxy surveys and from the cosmic microwave background's imprint. When we map millions of galaxies in 3 dimensions, patterns emerge that look like foam, with dense walls and empty cells. Simulations show that dark matter collapses into a similar pattern under gravity, because small fluctuations grow over time. Gas follows the same pattern, heating in shocks along filaments and cooling where it can settle. Galaxies light up the densest intersections, making the invisible skeleton partially visible. Filaments are not just lines on a map, and they are not merely decorative. They are channels of accretion that feed galaxies and groups, guiding gas and smaller halos inward. Over cosmic time, material flows along these structures, replenishing halos that would otherwise run out of star-forming fuel. The Milky Way's growth is part of that larger supply chain, and the rim is where inflow, outflow, and recycling meet. When we ask what lies beyond, we are also asking where the next meal comes from. Voids are not empty, and their emptiness is itself a clue. They have fewer galaxies and lower density, but they still expand and evolve, and they still contain dark matter and thin gas. Their existence shows that structure formation is a competition between gravity and expansion. In dense regions, gravity wins, pulling matter together, while in voids, expansion dominates and matter drains away. Even absence becomes a feature of the universe's architecture, a negative space that shapes everything around it. This is where the mysterious tone deepens, because the same unseen component appears at every scale. Dark matter shapes galaxies, halos, and the cosmic web, yet its nature remains unknown. We have mapped its gravity across scales, from dwarf galaxies to clusters and large-scale structure. We can predict its effects with precision, while lacking a direct detection in the laboratory. It is a dominant actor that never speaks. Candidates exist, but none is confirmed, and the search has reshaped modern physics. Weakly interacting massive particles were long favored, partly because they arise naturally in some theories beyond the standard model. Yet experiments deep underground, shielded from cosmic rays, have not found them. Axions remain plausible, motivated by solutions to other particle physics problems. But they are difficult to detect because their interactions are so faint. Modified gravity ideas attempt to remove the need for dark matter, yet they struggle to match all observations at once, especially in systems where lensing and dynamics disagree. So the rim becomes a gate to a larger question, and it is hard to avoid the philosophical weight. If most mass is invisible, then our picture of space is incomplete, even when our measurements are careful. If the universe can hide matter from light, it may hide other components as well. Fields, particles, or phenomena that barely interact with us. The edge of what we can see is not the edge of what exists. It is the edge of what our instruments can translate into certainty. Return to the central question in a new register, because it now carries more than geography. When we ask what lies beyond the edge of space, we are not only asking about distance, we are asking about the limits of observation and the possibility of unseen structure. The galaxy's boundary teaches that reality can extend beyond our senses, and that inference is sometimes the only honest path. At the edge of space, the sky doesn't end, and it never did. It changes from air to plasma, from plasma to interstellar medium, and now from starlight to dark scaffolding. Each step outward reduces what we can see, while increasing what we must infer. The universe becomes quieter in photons, yet louder in gravity. Build tension for the next chapter, because the logic forces a confrontation. If dark matter dominates the mass of the Milky Way, then the visible galaxy is only a tracer, bright, intricate, and incomplete. If dark matter dominates the universe, then most of cosmic history is written in an invisible language. The deeper we look, the more the universe asks us to trust indirect evidence and to accept that the most important structures may not glow. Now we turn from a galaxy's boundary to the universe's boundary of sight. The next edge is not set by where matter thins, and it is not a rim you could cross with enough fuel. It is set by time, expansion, and the speed of light, which limits what information can reach us. Beyond it may be more universe, but not more information, and that distinction matters. We leave the Milky Way's rim with a final reframing, because the chapter's answer is intentionally unsettled. The edge we sought was never a line in space. It was a limit in what starlight can reveal, and a hint that the strangest structures may be the ones we cannot see. The rim is not a wall. It is a threshold, and beyond it, the universe keeps its deepest inventory in the dark. Now we turn from a galaxy's boundary to the universe's boundary of sight, and the shift feels subtle until it suddenly isn't. This edge is not a rim of matter, not a place where stars stop, and not a fence you could ever touch. It is a horizon made by time, light speed, and expansion, an observational limit written into physics and enforced with quiet certainty. Start with a distinction that sounds semantic, but changes everything once you live inside it. The universe is all that exists, whether or not it can ever be observed by any instrument, now or in any future era. The observable universe is the portion whose light, or other signals, has had time to reach us, given the cosmos we inhabit. That difference is forced by two facts that never negotiate, even for the most ambitious telescope. The universe has a finite age, about 13.8 billion years, measured through multiple independent lines of evidence that agree in striking ways. Light has a finite speed, so information takes time to travel across any distance, even when space itself is changing. So the sky contains a built-in delay, and the delay is not a flaw in our instruments. Every photon is a message that left earlier, carrying the conditions of its birthplace like a timestamp, and sometimes like a fingerprint. The farther the source, the older the message, and the younger the universe appears in the image we receive. This is look-back time, and it is the core trick of cosmology, because it turns observation into archaeology. Nearby galaxies show mature stars, stable disks, and long-settled structures shaped by billions of years of mergers and feedback. Distant galaxies appear smaller, clumpier, and more actively forming stars, because we catch them while they are still assembling under harsher conditions. In deep-field images, the visual story becomes almost physical, as if the screen were layered glass. The foreground is filled with bright, well-ordered spirals and elliptical galaxies. Their light relatively recent, and their shapes familiar to our eyes. Farther back, the scene grows crowded with faint smudges and irregular knots. Star-forming regions blazing in ultraviolet, then reddened by distance and dust. Some of those faint points are magnified by chance, because gravity itself can act like a lens. Massive galaxy clusters bend spacetime and focus background light, stretching distant galaxies into arcs and thin streaks. Nature's own telescope, drawn in luminous curves. Even that visual distortion is information, a reminder that geometry and gravity shape what we can see. Distance becomes a time machine, but only in one direction, and that one-way nature matters. We can see the past because light arrives late, and the delay grows with distance through an expanding cosmos. We cannot see the future because no signal can arrive early, and causality refuses to bend, no matter how clever our engineering becomes. The horizon is not a wall in space, and it is not centered on us by design or destiny. It is centered on us only because we are the ones doing the observing, standing at the tip of our own light cone. Any observer, anywhere, carries their own observable sphere, each one a private bubble of accessible history, carved out by the same physical rules. To make the time horizon concrete, we need a way to measure distance across the expanding cosmos. And distance itself needs careful handling. Astronomers use several definitions: light travel distance, co-moving distance, proper distance, because expansion makes a single word do too much work. The measurement begins with a simple observation that shows up in spectra like a signature, written in lines as crisp as barcodes. The light from distant galaxies is shifted toward redder wavelengths. Redshift is often described as a Doppler effect, and that is partly useful for intuition. If a source moves away through space, its waves are stretched, the wavelength grows, and the light shifts to red. But cosmological redshift is deeper than motion through space, because it is tied to the stretching of space itself, which changes the scale of everything the light crosses. In an expanding universe, space stretches while light is in transit, and the light is carried along by that changing geometry. The crests of the wave do not merely chase the observer through a static arena, as if the cosmos were a fixed stage. They are separated by expanding space, so the wavelength grows as the photon travels, and that growth accumulates steadily over billions of years. By the time the light arrives, the wavelength has been stretched by the growth of the space it crossed. The photon has not slowed down, and it has not taken a detour through hidden corridors. The ruler we use to measure its wavelength has changed, and the wave is stretched with it, an effect that sounds abstract until you watch it animate. This is why redshift is written as a ratio rather than a simple subtraction. A redshift of z means the wavelength is larger by a factor of 1 plus z, and the scale factor of the universe has changed by the same ratio. The same photon leaves as one color and arrives as another. Its identity intact, its energy reduced, and its story lengthened by expansion. That stretching also drains energy from the light, because photon energy is inversely proportional to wavelength. Longer wavelength means lower photon energy, so the arriving light is dimmer and cooler in a precise, quantifiable way. The universe does not steal energy like a thief. Rather, in an expanding space-time, the idea of global energy conservation becomes subtle, because there is no single universal clock defining total energy everywhere. Redshift becomes our ruler and our clock at once, and it is hard to overstate its importance. Higher redshift generally means greater distance when interpreted through a cosmological model that accounts for matter, radiation, and dark energy. Higher redshift also means earlier cosmic time, when the universe was denser, hotter, and more dominated by radiation and fast interactions, before galaxies settled into familiar forms. When astronomers take a galaxy's spectrum, they see familiar atomic lines, hydrogen, oxygen, calcium, shifted like musical notes transposed into a lower key. Those lines are not just decoration, they are anchors, and they remain recognizable across cosmic time. They tell us how much the universe has expanded since the light left, and they let us place the galaxy on a timeline with surprising precision. Now introduce expansion without turning it into a myth, because the word expanding invites the wrong picture. In the 1920s, Edwin Hubble and others found a pattern by combining distances to galaxies with measurements of their redshifts, and the result changed our place in reality. The farther a galaxy is, the faster it appears to recede, and the relationship is strikingly regular at nearby scales where measurement errors can be beaten down. This is the Hubble-Lemaitre law, and the historical naming matters because the idea was not born from one mind alone. Georges Lemaitre, a Belgian priest and physicist, derived the expanding solution from Einstein's equations and connected it to observed redshifts with rare boldness. Hubble's observational program, built on Henrietta Leavitt's Cepheid period, luminosity relation, provided the distance ladder that made the pattern undeniable, one rung at a time. Recession speed is proportional to distance, at least for relatively nearby cosmic scales where the relationship is approximately linear. The constant of proportionality is the Hubble constant, which sets an expansion rate and therefore sets a timescale, often compared to an expansion age of the universe. In rough terms, it tells you how quickly cosmic distances grow per unit distance, an expansion per megaparsec, expressed in kilometers per second per megaparsec. The key point is what that pattern does not imply, because the wrong picture is persistent and emotionally intuitive. It does not mean we are at the center of an explosion with galaxies flying through space from a single point. It means the expansion is happening everywhere, so every observer sees distant galaxies receding in a similar way, and the symmetry is built into the geometry. Use an analogy that stays honest and limited, because analogies can mislead if they become too literal. If space expands like a stretching grid, every point sees other points move away as the grid lines lengthen. No point is privileged, and the grid itself is what changes. Distances increase because the metric changes, not because objects are propelled through a pre-existing emptiness. On screen, this is where a simple animation can do what paragraphs struggle to do. A lattice of points drifts apart as the background grid stretches, and the viewer sees that every point can claim to be in the middle. The expansion is not a motion within space, it is a change of space, and the difference is the difference between intuition and cosmology. This expansion changes the meaning of how far in a way that feels unfair, because intuition expects one distance to rule them all. The light travel time is not the same as the present-day distance, and the difference grows huge at high redshift, where the scale factor has changed dramatically. While the photon travels, the space between source and observer continues to expand. So the photon is crossing a moving target, and the finish line keeps sliding away. So the observable boundary is not simply 13.8 billion light-years away, even though the universe is 13.2 billion years old. The most distant light we can see today comes from matter that is now much farther away, carried outward by the expansion that happened after the light left. The observable radius is about 46 billion light-years, a number that sounds impossible until you remember the journey happened in an expanding arena. That number is not a contradiction, and it does not require exotic shortcuts. It is a consequence of expansion during the photon's journey, combined with the fact that light-year is a distance unit, not a time unit. Light can start close, travel for 13.8 billion years, and arrive from a region now far beyond 13.8 billion light-years, because the intervening space grew while the photon was in flight. If you could freeze the universe at the moment the photon was emitted, the source would be much nearer than it is today. If you unfreeze it and let expansion run, the gap widens while the photon is en route, and the geometry keeps evolving. The photon still moves at c locally, but the distance it must cover keeps changing, and that changing distance is the heart of the paradox that isn't. The observable universe can be finite even if the universe is infinite, and that distinction is conceptually clean. Infinity is about total extent, and it is a statement about the whole manifold, whether or not it ever repeats or curves back. Observability is about causal contact, limited by time and light speed, and therefore limited by the history of expansion, which decides what has had time to reach us. This is where the famous edge becomes less like a border and more like a rule. We do not stop because space ends, or because matter runs out like land at an ocean cliff. We stop because the universe has not had enough time to send us older light, and because earlier epochs were not transparent to photons, no matter how long we wait. Now move to the eerie boundary that looks like a surface, because the sky eventually changes character. If we look far enough back, galaxies thin out, not because they vanish, but because their light becomes faint and stretched beyond what our eyes evolved to see. Then the sky fills with a nearly uniform glow that comes from all directions. A background that seems to sit behind everything, like a dim curtain lit from within. That glow is the cosmic microwave background, the CMB, and it is one of the most profound images in science. It is relic radiation from the early universe, released when the cosmos first became transparent and then carried forward by expansion. It is not the light of stars, and it does not come from galaxies. It is the afterglow of a hot beginning, cooled by expansion into microwaves, and it surrounds us because it is woven into the history of space. Place it in time with one clean anchor, and then let the implications unfold. About 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen. This event is called recombination, though it was really the first stable combination on a cosmic scale, and it changed the universe's optical properties almost overnight. Before recombination, the universe was a plasma, a seething mixture of charged particles and photons. Free electrons scattered photons efficiently through Thomson scattering, so light could not travel far without being redirected, randomized, and thermalized. The cosmos was opaque, like a dense fog that keeps you from seeing across a room. Except the fog was everywhere, and the room was the whole universe. In that plasma, photons and matter were tightly coupled, trading energy and momentum constantly in a near-perfect thermal equilibrium. Pressure from radiation fought gravity, and the mixture behaved like a fluid with sound waves rippling through it, driven by tiny density differences. The early universe was not silent. It had oscillations, compressions, and rarefactions, patterns that later become visible in the CMB and later still in the distribution of galaxies. At recombination, that fog lifted, and the change was dramatic. With fewer free electrons, photons stopped scattering constantly, and the mean free path of light became enormous, suddenly spanning cosmic distances. Light decoupled from matter and began to stream freely through space, carrying a snapshot of the universe at that moment, including its temperature, density ripples, and motion. Those photons are still traveling, and they are arriving now from every direction, like an ancient rain. The universe expanded while they traveled, stretching their wavelengths by a factor of roughly 1,000, and cooling them with mathematical regularity. What began as hot, visible, and infrared radiation is now microwaves, cold enough to be measured by instruments cooled to near absolute zero, where the detectors themselves stop adding heat noise. Today, the CMB has a temperature of about 2.7 Kelvin, and that number is not a guess. It is measured as a near-perfect black-body spectrum, one of the cleanest signals in all of science, and it is astonishingly smooth. In plain terms, it matches the curve you would expect from an ideal thermal source, as if the universe once glowed like a hot ember and has been cooling ever since, its heat diluted by expansion. The discovery has its own quiet drama, and it fits the theme of horizons made of time. In 1965, Arno Penzias and Robert Wilson found an unexplained microwave hiss in their antenna, a noise that would not go away even after they checked equipment and cleaned out nesting pigeons. Nearby, theorists had predicted a relic background from a hot, early universe, and the pieces clicked together, an accidental detection of the oldest light we can see. So the CMB becomes our wall of light, but it is not a physical barrier you could crash into. It is the oldest light we can see directly, and it arrives from what is called the last scattering surface, a phrase that sounds like geography but is really history. It is the limit set by the universe's early opacity, not by an edge in space, and it marks the moment photons finally stopped ricocheting. The phrase surface is a trick of perspective, and it is worth lingering on it. We see the CMB as a shell around us because the photons come from a particular time, not a particular place, and time slices look like spheres from inside. In every direction, our line of sight eventually reaches the moment when the universe first became transparent, and that moment draws a sphere in our sky, even though the emitting matter is not arranged as a literal shell. The CMB is also not perfectly uniform, and that imperfection matters more than the uniformity. Tiny temperature differences appear across the sky at the level of tens of microkelvin, variations so small they sound like nothing, and yet they are measurable. Yet those faint mottles are the seeds of everything structured. Galaxies, clusters, and the long filaments of the cosmic web, all emerging from slight early imbalances. Explain the seed idea without losing the thread, because gravity needs only a slight advantage. Slightly denser regions had slightly stronger gravity, so they pulled in more matter over time, and the imbalance grew. Over billions of years, gravity amplified those small differences into galaxies, clusters, and the cosmic web, turning tiny early ripples into the large-scale architecture we map today, and turning microkelvin patterns into megaparsec structures. The anisotropies also encode early universe physics, and they do it in a way that is surprisingly precise. They reflect sound waves in the primordial plasma, acoustic oscillations driven by the push of radiation pressure and the pull of gravity, with dark matter providing extra gravitational wells. When photons decoupled, those oscillations were frozen into the radiation, and their angular pattern became a fingerprint of cosmological parameters, readable through power spectra rather than photographs. That fingerprint shows up as a characteristic scale on the sky, a preferred size for the hot and cold spots. It tells us about the geometry of space, because curvature changes how physical sizes project into angles, bending the relationship between size and apparent separation. It also tells us about the composition of the universe, because baryons, dark matter, and radiation affect how the early fluid oscillated, shifting the heights and spacing of the peaks in ways models must match. Now tie the fingerprint to actual missions, because this edge is mapped, not imagined. Kobe first detected the CMB's blackbody spectrum with stunning clarity, and then it revealed the first anisotropies, faint but real. WMAP mapped them with much higher precision across the full sky, turning the mottled pattern into a quantitative tool that could discriminate between competing cosmological models. Planck refined the map further, measuring temperature and polarization with exquisite detail and lower noise. And the resulting image looks almost like textured paint. Polarization adds another layer of information, because it records the directionality of scattering and the motion of the early plasma, separating patterns into distinct modes. These missions turned the CMB from a discovery into a dataset, and the dataset into a set of constraints, with uncertainties small enough to feel almost audacious. They helped pin down the universe's age, composition, and geometry, and they did it with an almost unsettling confidence. From the CMB, we infer a universe dominated not by ordinary atoms, but by dark matter and dark energy, with ordinary baryons as a minority component. We also infer that space is very close to flat on large scales, at least within the limits of our measurements, which is a geometric statement about the whole cosmos, not just what we can see. The CMB also reframes what beyond means, because it marks a boundary in electromagnetic visibility. Beyond it, there is no older light that can reach us directly in photons, because earlier photons were trapped and scattered, losing directional memory. There may be neutrinos, gravitational waves, or other messengers, but ordinary light cannot carry earlier images, because earlier light was trapped and scattered, and the universe kept its earliest scenes behind a veil. So the edge becomes a question about beginnings, not a border in space you could approach with engines. We can ask what happened before recombination, but we cannot see it with telescopes tuned to light, no matter how large the mirror becomes. We can only infer it through models and indirect traces, using the CMB as a boundary condition and checking every inference against the sky we actually measure. Even that inference is disciplined, because the models must match what we actually measure. The pattern of anisotropies is not random decoration. It is a coded record of physical processes, and the code is unforgiving. When we change a parameter in the model, matter density, expansion rate, curvature, the predicted pattern shifts, and the sky itself becomes the judge, accepting some stories and rejecting others. Now define horizons clearly, because the word horizon hides multiple limits that sound similar but behave differently. The particle horizon is the maximum distance from which light has reached us since the beginning. Given the universe's expansion history, it defines what is observable today, and it grows as time passes and more light has time to arrive, widening our accessible past. The event horizon is different and more unsettling because it points forward rather than backward. It is the boundary beyond which events will never be able to affect us, even given infinite future time, because the expansion can outrun communication. It depends on how expansion evolves, and in particular, on whether expansion accelerates strongly enough to isolate regions permanently, turning once shared space into separate islands of causality. In a universe with accelerating expansion, the event horizon becomes real in a practical sense. Some galaxies are visible today because their past light is already on the way, already inside our past light cone, and already arriving at our telescopes. Yet their future light may never reach us, because space will expand too fast for new photons to make progress across the growing gap. And the stream of information will eventually thin to nothing. This is not about speed limits for galaxies through space, and it is not a violation of relativity. It is about the growth of the space between us and them, described by the scale factor in cosmology, which can change faster than intuition expects. Expansion can make distance increase faster than light can close the gap, because the rule, nothing moves faster than light, applies locally, not to the growth of space itself, which is a property of the metric. So there are two kinds of beyond, and they are easy to confuse if you picture them as the same wall. Beyond the particle horizon is outside our past light cone, so we cannot see it yet, no matter how long we stare or how long the universe lasts. Beyond the event horizon is outside our future causal reach, so we may never exchange signals with it, even in principle, and the separation is permanent. These horizons are not fixed walls, and their motion is part of the story. As time passes, the particle horizon grows and we see more, and the observable sphere expands into previously unseen regions, adding new galaxies to our maps. But the event horizon can remain finite, and it can even tighten what remains causally connected, limiting the set of galaxies we can ever influence, and eventually limiting what can ever influence us. On a visual timeline, the difference is stark. The past light cone opens backward, widening into the ancient universe, and it defines what can be observed now, including the CMB at its far edge. The future light cone opens forward, but accelerating expansion can pinch what remains reachable, like a corridor that narrows as you walk. And the narrowing is not psychological, it is geometric. Now bring the central question back with sharper stakes, because edge is really about information. When we ask what lies beyond the edge of space, we are not only asking what lies farther out, beyond the last visible galaxies. We are asking what lies outside our ability to receive information, and therefore outside our ability to test ideas directly, which is where science becomes careful and humble. The observable universe is a boundary that moves with time and technology, but it is still a boundary. Better telescopes can collect fainter light and push deeper into cosmic history, and improved detectors can measure subtle signals with less noise, pulling structure out of darkness. They cannot see before the universe became transparent to light, because opacity is not a problem of sensitivity. It is a problem of physics, and physics does not yield to larger mirrors. Even within transparency, expansion imposes a hierarchy of eras that we read like layers in rock. Nearby space shows the present, with galaxies shaped by long evolution and environments shaped by gravity and feedback from stars and black holes. Farther out we see earlier stages. When galaxies were assembling, Star formation was more intense, and black holes were growing rapidly in young cosmic centers, lighting up as quasars against the dark. At the farthest limit, the CMB marks a last scattering surface, and it looks like a shell around us because we see it in all directions. It is really a time slice, the same cosmic moment seen from every angle, projected onto the sky as a sphere, and the projection is a consequence of geometry. The shell is not a boundary of space, it is a boundary of visibility, and it is the oldest electromagnetic record we possess. That shell is not the end of the universe, and it is important not to let the image trick you. It is the end of the universe's visible record in photons, the earliest photograph the cosmos allows, and even that photograph is filtered through physics. Beyond it, the story continues, but the medium of the story changes, and our access becomes indirect, mediated by models and by messengers that are harder to catch. This is where the tone turns from travel to inference, because the edge is not a cliff you could cross with enough fuel. It is a horizon in time, and time is not something a spacecraft can outrun. Even if it could travel near light speed and survive the journey, you can move through space, but you cannot move into the past light that never had a chance to reach you, and you cannot force the universe to send signals it never released. So the documentary's most famous edge becomes a disciplined kind of mystery, the kind science respects. We can measure the CMB's temperature and its tiny variations, and we can map them with increasing precision, sharpening the mottled pattern into a cosmic dataset. We can connect those variations to the growth of structure and to the contents of the cosmos. And we can test the consistency of the whole picture, looking for cracks that would reveal missing physics. Yet we still face a blankness behind the light, and the blankness has a cause. Before recombination, the universe is hidden behind scattering, and photons cannot carry clean images because every direction is scrambled by collisions. Earlier still, the physics becomes more extreme. Temperatures rise, densities soar, and our tested theories begin to strain as we approach conditions we cannot reproduce completely on Earth, where experiments are bounded by energy and scale. Build tension with one clean statement and let it land. Beyond the CMB, there is no image, only equations and indirect evidence, and the difference is not philosophical. The edge is not a border in space. It is a limit in knowledge set by the universe's own history, by what it allowed to travel and when, and by what it kept trapped until it was too late to photograph. Now pivot toward the next chapter's promise, because models are where beyond becomes a meaningful question again. If the observable edge is a time horizon, what does the universe look like beyond it in principle, even if we cannot see it directly? We step from observation into models, where geometry, curvature, and global shape decide what beyond can mean, and where the same equations that predict the CMB also hint at the larger stage. Hold the conclusion theme in compressed form, so the chapter closes like a door that still leaves light under it. The edge of space is real, but it is a threshold, not a final wall, and it is defined by causality rather than geography. The deeper edges are horizons in time and causality, and they shift as our methods improve and our measurements sharpen, revealing more detail even when the ultimate limit remains. End on the moving edge, because it keeps the series hook alive without pretending the mystery is unsolved by effort alone. At the edge of space, the sky doesn't end. It changes into a record of earlier time, and the farther we look, the stranger the rules become, until the universe itself refuses to show us more in light and invites us to keep going with inference instead. At the edge of space, the sky doesn't end. It changes, and the change keeps escalating as our questions sharpen. The blue thins into indigo, indigo into black, and then the black itself becomes crowded with structure. Stars appear as pinpricks, then as swarms, then as a faint grainy fog that is not empty at all. Beyond galaxies and the observable horizon, the next question is not distance, it is shape. When we ask what lies beyond the edge of space, beyond stars, galaxies, and even the observable universe, what do we mean by beyond? Are we talking about more space, the limits of light and time, or a boundary to reality itself? Chapter 4 gave us a horizon made of time, drawn by light speed and expansion. Chapter 5 asks what the larger stage looks like, even if we never reach its far side. Start with the idea that geometry is not decoration in physics, because it sets the rules of what motion even means. In general relativity, space-time is the arena and the actor, a fabric that can flex and respond. Mass and energy do not merely move through space, as if space were a passive container. They curve space-time, and that curvature tells matter how to move. Einstein's insight was radical because it replaced a force with a geometry, and it did so with measurable consequences. A planet orbiting the Sun is not being pulled in the old Newtonian sense. It is following the straightest possible path, called a geodesic, through a curved space-time. Even light, which has no rest mass, follows these geodesics, and that is why gravity can bend starlight. The mathematics behind this is compact but profound, because it ties shape to substance in a single statement. Einstein's field equations relate the curvature of space-time to the stress-energy content within it. In plain language, energy density, pressure, and momentum flow all contribute to curvature. That means the universe's geometry is not an aesthetic choice. It is a physical outcome. This is the first step toward a new kind of edge, one that has nothing to do with walls. If space can curve, then straight ahead can be a path that bends without turning, like a great circle route on Earth. If space can curve globally, then the universe can be finite without having a boundary. The edge, in that case, is not a cliff. It is a closedness of the map. Separate two meanings of curvature before the story gets tangled, because the word hides multiple scales. Local curvature is the warping near stars, black holes, and galaxies, where gravity is strong enough to distort trajectories. It is measured by how clocks tick, how light bends, and how orbits precess. Global curvature is the average geometry of the universe on the largest scales, after local lumps are smoothed into a cosmic mean. Local curvature is obvious in principle, even if it is hard to measure precisely in practice. We see gravitational lensing as arcs and rings, where a galaxy cluster acts like a natural telescope. We see time dilation in GPS satellites, whose clocks must be corrected because they sit higher in Earth's gravitational field. We see the precession of Mercury's orbit, a historical triumph that helped confirm general relativity. Each effect is a local fingerprint of curvature. Global curvature is subtler because we only observe one region and we are embedded inside it. We infer it by comparing the universe's measured contents to the geometry that best fits the data. In the standard cosmological framework, the overall curvature is encoded by a parameter that compares total energy density to a critical value. If the total equals the critical density, space is globally flat in the simplest models. If it exceeds that value, the geometry tends toward closed, and if it falls below, it tends toward open. Now the documentary pivots from travelogue to geometry, because the edge may be a property of the whole. The question becomes whether the cosmos is open, flat, or closed. These words sound like doors, but they are mathematical labels for curvature. They describe how space behaves when you extend a ruler and keep going. In the simplest cosmological models, there are three classic geometries, each with a distinct intuition. An open universe has negative curvature, like a saddle surface extended into higher dimensions. A flat universe has zero curvature, like Euclidean space extended in 3 dimensions. A closed universe has positive curvature, like the surface of a sphere, but again in higher dimensions. To visualize this, imagine a grid painted onto space, with lines that mark straight directions. In flat space, the grid can extend forever without distortion, and squares stay squares. In curved space, the grid can't remain uniform, and the distortion accumulates with distance. Curvature is not a bump in space. It is the rule for how geometry behaves everywhere. Explain the difference with rules that viewers can test in their heads, because geometry becomes intuitive when it becomes a game. In flat geometry, the angles of a triangle add to 180 degrees. Parallel lines stay parallel forever, never meeting and never diverging. If you draw a circle, its circumference is exactly 2p times its radius. These are the quiet assumptions of everyday life. In curved geometry, those rules change, and the change is the clue. In positive curvature, triangle angles add to more than 180 degrees. Lines that start parallel can eventually meet, like longitudes on Earth that converge at the poles. Circles have less circumference than you would expect for their radius, because space is tighter than Euclid predicts. In negative curvature, triangle angles add to less than 180 degrees, as if the surface is stretched outward. Lines that start parallel can diverge, and they do so relentlessly, as though space is opening beneath them. Circles have more circumference than expected, because there is more room than Euclid allows. The geometry itself amplifies separation. These are not just classroom puzzles, because the universe itself can be the surface. If the cosmos is positively curved and closed, it can be finite in volume. It can still be unbounded, meaning there is no edge you can point to. You can travel without ever hitting a wall, yet still not have infinite space. This is a subtle idea, and it is worth lingering on the imagery it implies. Picture a spacecraft that never turns, never accelerates sideways, and never aims for home. It simply follows a geodesic, the straightest possible line in that geometry. In a closed universe, that path can eventually bring it back, not because it reversed course, but because space itself loops. If the cosmos is open, it is usually infinite in extent in the simplest models, because negative curvature does not naturally close on itself. If it is exactly flat, it can be infinite, but that is not the only option. Geometry and topology are different questions, and confusing them creates false certainty. The universe can obey Euclid locally and still be globally compact. Geometry is about local rules of distance and angles, the way rulers and protractors behave. Topology is about global connectedness, about whether space wraps and reconnects. A universe can be geometrically flat and still be topologically finite. It can look like ordinary space nearby, yet loop back on itself far away. This distinction has a history, because mathematicians learned long ago that shape and connectedness are not the same. A coffee mug and a donut can be continuously deformed into each other, because each has one hole. That is topology speaking, and it ignores the exact curvature at every point. Cosmology borrows that lesson and asks a daring question. Could the universe have a hole or a wrap in a way that changes nothing locally? Now widen the scale again without changing the question, because the evidence comes from the earliest light. The cosmic microwave background is not only a time boundary, it is also a measuring tape for curvature. It is the afterglow of the moment the universe became transparent, when electrons and protons combined into neutral atoms and photons finally traveled freely. Visually, the CMB is a sphere around us, a shell of ancient light arriving from every direction. On screen, it looks like a mottled globe, with hot and cold patches that differ by only tens of microkelvin. Those tiny variations encode density differences of roughly 1 part in 100,000. They are the seeds from which galaxies eventually grew. The CMB contains a characteristic physical scale set by sound waves in the early plasma. Before atoms formed, the universe was a hot ionized fluid, where photons and baryons were tightly coupled. Gravity tried to compress overdense regions, while radiation pressure pushed back, creating acoustic oscillations. When the universe cooled enough for recombination, those oscillations froze in place. That frozen imprint defines the sound horizon, a standard ruler with a calculable physical length. The same scale is also seen later as baryon acoustic oscillations in galaxy clustering, a faint preference for galaxies to be separated by that distance. If we know the physical size of that ruler, we can compare it to its apparent angular size on the sky. Curvature changes that mapping between size and angle. In a positively curved universe, light paths converge, and objects of a given size appear larger on the sky. In a negatively curved universe, light paths diverge, and objects appear smaller. In a flat universe, the Euclidean expectation holds, once expansion history is accounted for. The key is that geometry affects how angles translate into distances across cosmic time. This is why cosmology uses multiple probes, because curvature can masquerade as other effects if you only ask one question. The CMB gives a snapshot of early conditions, but it also depends on how the universe expanded afterward. Baryon acoustic oscillations provide a later time ruler that tracks the growth of structure. Supernovae provide a different kind of measurement, based on brightness rather than angular size. Observations now stack multiple rulers and candles to constrain the answer, and the result is remarkably consistent. Planck's CMB data, combined with baryon acoustic oscillations, points to a universe extremely close to flat. Type Ia supernovae add the expansion history that ties distances to redshift, because their intrinsic luminosity can be standardized. Together, they produce a coherent picture with small error bars. Behind that coherence is a practical triumph of instrumentation and analysis. WMAP first mapped the CMB with high precision, revealing the acoustic peaks in its power spectrum. Planck refined that picture with better angular resolution and sensitivity, and it measured polarization patterns as well. Each peak position and height encodes parameters like matter density, baryon fraction, and the tilt of the primordial spectrum. Curvature shifts the peak positions in a way that can be quantified. But near flat is not the same as infinite, and the difference matters for the edge. Near flat means the radius of curvature is very large compared to the observable universe. It means any global curvature is too gentle to detect within our horizon. A sphere can look flat on a small patch, and our patch may be tiny. To make that concrete, imagine standing on a vast planet with a radius millions of times larger than Earth's. The ground beneath your feet would look perfectly flat, and even careful surveying might detect no curvature. Yet the planet could still be finite, and you could still circumnavigate it in principle. Cosmology faces the same predicament, except our surveying tools are photons and statistical patterns. So the edge becomes a trick of scale, and scale is the one thing we can't step outside to check. If the universe is closed but enormous, we may never see enough of it to detect the curve. If the universe is flat but finite by topology, we may never see the wraparound. The data can tell us what the local patch looks like. It may never tell us the full shape of the whole. Introduce the limits of measurement before the mystery hardens into a claim, because uncertainty is part of the story. Cosmic variance means we have only one sky to measure. We cannot average over many universes to beat down the largest scale uncertainties. Horizon limits mean we cannot observe beyond our past light cone, even in principle. Some global properties are underdetermined because the universe gives us only one sample. The largest angular scales in the CMB correspond to the biggest physical modes, and there are only a few independent ones on a sphere. That scarcity makes the low multipoles noisy, not because our instruments are poor, but because statistics are unforgiving. It is a built-in limit, written into the geometry of observation. This is where topology enters as a hidden edge, because it offers a way for space to be finite without curvature giving it away. Imagine a video game world where walking off one side brings you back on the other. Locally it feels flat, and the rules of triangles look normal. Globally, it is finite because space repeats. In 3 dimensions, one simple example is a 3 torus, which is harder to picture but easy to describe. Each spatial direction wraps around, so traveling far enough in any direction returns you to your starting region. There is no boundary, but there is a finite volume. The edge is replaced by identification, by a rule that says distant points are actually the same point. A helpful visual is to start with a square map where the left and right edges are identified and the top and bottom edges are identified. A character walking right exits the square and re-enters from the left, as if the world was seamless. In 3 dimensions, the same identification happens with a cube, whose opposite faces are glued together in the mathematical sense. The result is a space that is locally ordinary but globally looping. A topologically wrapped universe would leave subtle fingerprints, because light would not have only one route. Light could take multiple paths around the cosmos, arriving at us from different directions after different travel times. We might see the same region of space in different directions at different look-back times. The sky could contain repetitions that are not coincidences. This possibility turns the cosmos into a hall of mirrors, but with mirrors made of geometry rather than glass. A galaxy cluster could appear twice, once as it was billions of years ago and once as it was later, depending on the path length. The repetition would not be identical in detail because the object evolves, but the large-scale arrangement could betray the connection. The question becomes whether the universe is big enough to hide such echoes. One proposed test is the search for matched circles in the CMB, a beautifully specific prediction. If the last scattering surface intersects itself due to wraparound, it could produce pairs of circles with the same temperature pattern. These circles would be separated on the sky, but share correlated fluctuations. Finding them would be evidence that space is finite and multiply connected. The logic is geometric and visual, which makes it ideal for a documentary. The last scattering surface is like a sphere centered on us, marking where the CMB photons last interacted with matter. In a wrapped universe, that sphere can overlap with itself, because far away can be the same place by identification. Where the overlaps occur, the same physical region is seen in 2 directions, producing matching rings. The search has been conducted with WMAP and Planck data, and it has not found convincing matched circles. That non-detection rules out some small topologies, where the RAP scale is smaller than the observable universe. It does not rule out larger RAP scales, where the repetition would lie beyond our horizon. Absence of evidence becomes a statement about minimum size, not about impossibility. There is also the practical challenge that the CMB is not a pristine photograph. Foreground emission from our own galaxy must be modeled and subtracted, and that subtraction can leave residuals. Instrument noise and beam effects must be carefully characterized because false correlations can appear. Even the thickness of the last scattering surface blurs patterns slightly, softening the sharpness of any matched signature. Topology also includes stranger possibilities than a simple torus. and some are more deceptive. Space could be connected in ways that are hard to visualize, with twists and identifications that change orientation. Some topologies could mimic others within our limited view. The universe could be globally finite in a way that hides behind near-flat geometry. This is where the word shape becomes slippery, because it is not only about curvature. Two spaces can have the same local curvature and still differ in global connectedness. From inside, both can look like an endless grid of galaxies, fading into redshift and darkness. Only by catching a repetition, or by measuring subtle correlations, could we hope to tell them apart. Now connect this to inflation, because inflation is the engine that makes near-flatness plausible. Inflation proposes a brief era of accelerated expansion in the early universe. It stretches space so rapidly that any initial curvature is diluted, like wrinkles pulled taut. It also stretches tiny quantum fluctuations into macroscopic seeds for structure. Inflation was proposed in the early 1980s to address problems that looked like coincidences in the hot Big Bang model. One was the horizon problem, the puzzle of why the CMB is so uniform across regions that seem causally disconnected without inflation. Another was the flatness problem, the question of why the density is so close to the critical value. A third was the absence of relics, like magnetic monopoles, which some particle theories predicted, but we do not see. Inflation explains why the observable universe looks so uniform in temperature, because it changes what causally connected means. Regions now far apart were once close enough to share thermal equilibrium before inflation expanded them beyond each other's horizons. The smoothing is not magical. It is a consequence of starting with a small connected patch that had time to equilibrate. Inflation also explains why the CMB anisotropies have the pattern we see, with nearly scale-invariant fluctuations. Quantum fields cannot be perfectly quiet, even in a vacuum, and their fluctuations are unavoidable. During inflation, those fluctuations are stretched to astrophysical scales, becoming tiny density differences. Later, gravity amplifies them into the cosmic web of filaments and voids. On screen, this is where the visuals can become almost tactile. A tiny patch of space, smaller than an atom, swells into something larger than a galaxy, and then larger than our entire observable region. A grid drawn on that patch becomes smoother as it expands, its curvature flattening as the scale grows. The viewer can feel the way inflation makes the universe look simple, even if its origins were complicated. Inflation does not force the universe to be infinite, but it can make it effectively enormous. It can push any global curvature radius far beyond what we can observe. It can also make a finite topology hard to detect, by stretching the RAP scale beyond our horizon. Inflation is a reason the edge keeps retreating as we learn to see farther. There is a delicate point here, and it matters for honesty. Inflation makes predictions that are broadly consistent with the data, but the detailed model space is large. Different inflationary potentials can produce slightly different spectral tilts, tensor amplitudes, and non-Gaussian signatures. Observations constrain these possibilities, and the constraints are tightening, but the core idea remains a framework rather than a single, nailed-down mechanism. Build tension around the word edge, because this chapter is about replacing a wall with a loop. If space is closed by curvature, you can travel forever without meeting an end. If space is flat but wrapped, you can travel far enough and return. In both cases, the edge is not a place. It is a property of the map. This reframes the central question in a sharper way, and it also exposes an assumption we rarely notice. When we ask what lies beyond the edge of space, we may be asking a question with no geographic answer. Beyond might mean more of the same, repeating or curving back. Beyond might mean nothing at all, because beyond assumes a boundary that may not exist. But the mystery deepens because topology can disguise itself as ordinary space, and curvature can hide behind scale. A wrapped universe can look infinite if the wrap scale is huge. A curved universe can look flat if the curvature radius is enormous. Our observations are limited to one horizon-sized bubble, and that bubble may be too small to reveal the global design. Introduce the horizon limits again, now as a constraint on global shape rather than merely on distance. The particle horizon sets the maximum co-moving distance from which light has reached us since the Big Bang. Even if the universe loops, we only see the part whose light had time to arrive. Even if the universe is closed, we may not see far enough to notice the curve. The language of co-moving distance matters here because the universe expands while light travels. Co-moving coordinates factor out that expansion, letting us talk about positions in the cosmic grid. The particle horizon is then a limit on how much of that grid is in causal contact with us. It is not an edge in space, it is an edge in our past light cone. Cosmic variance adds a second constraint that is less intuitive but equally strict. And it comes from the fact that we are stuck with one realization. The largest scale modes in the CMB are few in number, and they are noisy because there are only so many independent patches on a sphere. This limits how precisely we can measure curvature and topology using the biggest patterns. The universe's largest features are the hardest to measure because we are inside them. So some questions may be fundamentally underdetermined by data, even with perfect instruments. We can constrain curvature to be near zero, but we may never prove it is exactly zero. We can rule out small topological identifications, but we may never rule out huge ones. The edge may be a question that physics allows, but observation cannot close. This is not a failure of science, and it is not a license for anything. It is a boundary condition on what can be inferred from one cosmic sample. It forces humility in how we talk about infinity. It also forces precision in what we mean by evidence, because evidence always lives inside an observational horizon. Now connect back to earlier chapters, because the theme of edges has been repeating at every scale. The Kármán line was a convention, not a wall, drawn where aerodynamics gives way to orbital mechanics. The heliopause was porous and shifting, not a fence, shaped by solar wind and interstellar pressure. The Milky Way's rim depended on whether we followed light, gas, or gravity. The observable universe was a horizon of time, not a border of matter. Global shape is the next escalation of that pattern, and it is the most abstract edge yet. The edge may be a coordinate artifact, a misunderstanding of what it means to move in curved space. Or the edge may be hidden in topology, where space ends only by reconnecting. The deeper we go, the more edge becomes a statement about knowledge, not geography. Hold a backbone sentence that ties the whole chapter together, because the viewer needs a single beam through the complexity. If the universe is unbounded, then the edge is not a place you can reach. And if the universe is finite, then the edge may be a rule that makes distant places identical. That rule could be curvature closing the geometry, or topology identifying points across vast distances. At this point, it is worth asking a quiet, unsettling question. If the universe loops, what would it mean to go far enough when the expansion of space itself changes every journey? Could a traveler ever complete a circumnavigation, or would the goal recede as the cosmos stretches? The geometry might allow a return, but the dynamics might prevent it. Now pivot to the next chapter's promise, because inflation does not stop at geometry. If inflation happened, it may not have happened only once. Some versions of inflation are eternal, with inflation ending in some regions while continuing in others. That creates a patchwork of bubble universes, each with its own local conditions. So the question of beyond shifts again, and the shift is the natural continuation of this chapter's logic. It stops being only about where space goes. It becomes about how many spaces there are. If our observable universe is one region where inflation ended, then beyond our horizon could be other regions with different histories. End by tightening the series' conclusion theme without resolving what cannot be resolved. The edge of space is real, but it's only the first threshold. The deeper edges, curvature, topology, and the limits of measurement are not walls in the universe, but horizons in knowledge. What lies beyond may be more universe, a loop back to where we began, or a larger multiverse where our patch is only one outcome. And the mystery is that the edge keeps moving as we learn to see farther. At the edge of space, the sky doesn't end. It changes, thinning from blue to black as scattering fades away. And if you keep going far enough, the universe doesn't just get darker, it gets stranger, because the next boundary is not made of rock or gas, but of causality. Chapter 4 gave us a horizon made of time, drawn by the finite speed of light and the finite age of the cosmos. Chapter 5 asked whether space can curve, wrap, or repeat without any boundary, like a globe with no edge. Now we cross from the edge of observation into the edge of theory, where beyond becomes a question about causality. Define the word carefully because it misleads almost everyone at first, including people who know the equations. In cosmology, beyond the universe rarely means outside in space, as if the cosmos sits in a larger room. It means regions that exist in the same space-time, yet remain causally disconnected from us. Causal disconnection is not a metaphor, and it is not a failure of engineering or ambition. It is the statement that no signal traveling at or below light speed can ever cross the gap. Expansion and horizons can separate regions so completely that they are forever outside each other's light cones. To picture a light cone, imagine a flashlight switched on in the dark, then let time flow upward like a rising column. The beam spreads outward, marking every location that could possibly be reached by that light. Anything outside that cone is not merely far away, it is unreachable, even in principle. This is the climax of the series' central question, because beyond stops being a direction and becomes a limit on information. When we ask what lies beyond the edge of space, beyond stars, galaxies, and even the observable universe, are we talking about more space, the limits of light and time, or a boundary to reality itself? Here, more can exist without ever becoming information. Start with the horizon language from Chapter 4, because it is the cleanest bridge between what we see and what we can never see. The particle horizon marks what has had time to reach us since the beginning, given the universe's expansion history. The event horizon marks what can ever reach us, even with infinite future time. Those two horizons sound similar, yet they point in opposite temporal directions, one backward, one forward. The particle horizon is a historical boundary, drawn by the age of the cosmos and the speed of light. The event horizon is a destiny boundary, drawn by the future behavior of expansion. The event horizon is the more unsettling edge, because it points forward into a future that can shrink our accessible world. If expansion accelerates, there are places whose light is arriving now, yet whose future signals will never arrive. A galaxy can be visible in our telescopes, while its later history becomes permanently inaccessible. Visually, this is the eerie moment when a bright spiral remains in view, but its timeline is cut. We still receive photons that left long ago, when the galaxy was closer in co-moving terms. Yet the photons it emits tomorrow for it, may never cross the stretching gulf. Now introduce dark energy as the modern driver of edges, because it changes the fate of knowledge. Observations of distant Type Ia supernovae, baryon acoustic oscillations, large-scale structure growth, and the CMB imply late-time accelerated expansion. In the simplest model, a cosmological constant makes the expansion approach an exponential regime. Historically, the cosmological constant has a strange biography, introduced by Einstein, discarded after Hubble's expansion, then resurrected by late 1990s supernova data. In equations, it behaves like a constant energy density of the vacuum, with negative pressure. In plain language, it acts like a gentle push built into space itself. Acceleration matters because it reshapes the causal map, not just the distances on a chart. When expansion decelerates, light has a chance to catch up, and horizons can grow. When expansion accelerates, the universe can create a permanent boundary, a true event horizon. In that regime, the universe becomes an archipelago of causality, many islands separated by an ever-widening sea. Bound structures like the local group remain gravitationally bound, while distant galaxies slip beyond reach. Over cosmic time, more of the observable universe becomes unobservable in principle, not just in practice. The visuals here are slow and quiet, the cosmic web like faint mist, filaments stretching, clusters dimming, and the sky gradually losing its deep background of galaxies. It is not a sudden catastrophe, but a long subtraction. The universe does not end. Our access to it narrows. This is not galaxies breaking relativity by outrunning light through space, and it is crucial to say that clearly. It is the metric expanding so that proper distances grow faster than light can close them. Relativity limits local motion through space, while cosmology describes how the stage itself can stretch. In general relativity, speed is local, measured by nearby observers with rulers and clocks. A distant galaxy can recede superluminally in terms of changing proper distance, without any object locally exceeding light speed. The paradox dissolves once you remember that space-time is the object doing the expanding. So beyond can mean a region that still exists, still evolves, and still contains matter and radiation. Yet it can never send us a new photon, neutrino, or gravitational wave after some finite time. The edge is not a wall. It is a one-way loss of causal contact. That one-way quality is what makes the event horizon feel like a physical boundary, even though nothing is there. You can point a telescope toward a galaxy, measure its redshift, infer its mass, and still be cut off from its future forever. Knowledge becomes time-limited, and the universe becomes a story with missing chapters. Now connect this to inflation, because inflation is the earlier, more violent cousin of dark energy. Inflation was introduced in the early 1980s to explain why the universe looks so flat, so uniform, and so free of unwanted relics. It also provides a mechanism for seeding structure through stretched quantum fluctuations. The horizon problem is the classic motivation, and it is almost cinematic in its simplicity. The CMB is uniform across the sky to about 1 part in 100,000. Yet widely separated regions of that early plasma should never have exchanged light or heat in a non-inflating Big Bang. Inflation resolves that by changing the order of events, not by adding a new material boundary. It says those regions were once close enough to equilibrate. Then space expanded so rapidly that they were flung far apart. The uniformity is inherited from an earlier time when nearby meant something different. Flatness is the second clue, and it is geometric rather than thermal. In the Friedmann equations, any small deviation from spatial flatness tends to grow over time in a decelerating universe. Inflation reverses that tendency by diluting curvature. driving the geometry toward flatness the way a balloon's surface looks flatter as it inflates. Inflation also sweeps away relics, which is a subtle but important point in early universe physics. Grand unified theories often predict heavy topological defects, like magnetic monopoles, that would overclose the universe if abundant. A long enough inflationary phase can dilute such relics to near nothing, leaving a cleaner cosmos behind. Inflation itself has strong empirical support as a framework, even if the microphysics remains uncertain. The CMB's near-flat geometry, its nearly scale-invariant spectrum, and the phase coherence of acoustic peaks fit inflationary expectations. Many alternative ideas struggle to match that full pattern without fine-tuning. The acoustic peaks are especially telling because they encode a precise rhythm from the early plasma. Tiny density perturbations drove sound waves in the hot photon boron fluid, then froze into a pattern at recombination. Inflation predicts those perturbations began as coherent, nearly Gaussian fluctuations, and the CMB largely agrees. But the chapter's question is not only whether inflation happened, because that is already a constrained scientific claim. It is whether inflation ends everywhere, or whether it can continue in some regions. That distinction is where beyond our universe becomes a multiverse claim. Eternal inflation is the idea that inflation is generically self-reproducing, because quantum fluctuations can compete with classical rolling. In some patches, the inflaton field rolls down its potential and inflation ends. In other patches, fluctuations kick it upward, keeping inflation going longer. The result is a space-time that never fully exits inflation, while pockets of non-inflating space appear like bubbles. The background keeps inflating, and the bubbles keep forming, each one a local ending. It is a strange picture, an ending that happens repeatedly, without the overall process ever finishing. Each bubble is a region where inflation ended, and reheating filled space with hot particles. Inside a bubble, standard hot Big Bang evolution begins, with nucleosynthesis, recombination, and the later formation of galaxies. Our observable universe would be a small part of one such bubble. Reheating is the bridge from smooth accelerated expansion to a universe full of stuff. The inflaton's energy must be transferred into ordinary particles, raising the temperature and producing a hot plasma. In visual terms, a cold, empty, rapidly expanding space becomes suddenly bright with radiation, like a dawn written into physics. The key point is what is supported and what is speculative, because the words can slide too easily. Inflation's broad successes are tied to observable signatures in the CMB and large-scale structure. Eternal inflation is a further step that depends on the shape of the inflationary potential and quantum behavior in curved spacetime. Even within inflationary theory, eternal inflation is not a single model with one clear prediction. Some potentials make it likely, others avoid it, and some require assumptions about initial conditions. The evidence for inflation does not automatically become evidence for an infinite multiverse. Still, the logic is hard to ignore once you accept accelerated expansion in the early universe. If inflation can last long enough to erase curvature and homogenize a region, it can also last long enough to produce regions we will never see. The same mechanism that solves the horizon problem can generate new horizons. This is where the word beyond becomes almost literal again, but in the language of space-time diagrams. Our bubble has its own causal structure, and the inflating regions outside it recede faster than any signal can chase. The boundary is not a shell in space, it is a boundary in causal accessibility. Now widen the scale again without changing the question, because the multiverse is an edge of explanation. If bubble universes exist, they may have different vacuum states, different symmetry breakings, and different effective constants. The laws could share a deeper structure, while their low-energy outcomes differ. In particle physics, symmetries can break in more than one way, and the vacuum can settle into different configurations. A field can have multiple minima, like a landscape of valleys, and where it lands determines what particles are light, what forces are strong, and what interactions are allowed. In a multiverse picture, different bubbles could cool into different valleys. This is where the landscape idea enters, and it is where cosmology becomes most controversial. In some approaches to string theory, there are many possible vacuum solutions, each corresponding to a different way extra dimensions can compactify. Each vacuum can yield different particle spectra, coupling strengths, and cosmological constants. The historical background matters because it explains why this idea arrived with such force. String theory began as a candidate for unifying gravity with quantum mechanics, and it naturally requires extra dimensions. Once you allow many ways to curl those dimensions, the number of possible low-energy worlds can become enormous, far beyond a simple menu. The landscape is attractive because it offers a framework for why parameters look fine-tuned, especially the small but non-zero value of dark energy. If many vacua exist, then some will allow long-lived stars, chemistry, and observers. The observed values might be selection effects within a larger ensemble, rather than unique predictions from first principles. Yet even that attraction carries a sharp edge, because selection arguments can become slippery. If you can always say, "We see this because otherwise we wouldn't be here," you risk explaining away the need for deeper mechanisms. The question becomes, does the landscape predict anything specific, or does it merely accommodate? But the landscape is also dangerous because it can weaken the predictive core of physics. If almost any low-energy outcome exists somewhere, then matching our universe becomes less impressive. The theory risks becoming a catalogue of possibilities rather than a generator of sharp, testable numbers. Testing is the central tension, and it must be stated plainly without theatrical certainty. We cannot travel to other bubbles, and we may never receive signals from them. If the multiverse is real, it may be real in a way that is observationally silent. That silence is not absolute, and this is where the chapter's suspense stays grounded in actual data analysis. Some bubble scenarios predict collisions between bubbles in the early universe, when space was smaller and bubble walls could intersect. A collision could leave an imprint in the CMB, like a disk-like feature or a specific pattern of anisotropy and polarization. A collision imprint would not look like a cartoon bruise, but like a subtle statistical asymmetry. It could shift temperature fluctuations in a circular region, alter the E-mode polarization pattern, or create a localized departure from Gaussian randomness. The signature depends on the collision's energy and geometry, so the search must be broad. Scientists have searched for such signatures in WMAP and Planck data, using both targeted templates and blind anomaly hunts. They look for statistically unusual circular features, anisotropic power, or localized departures from Gaussianity. The results so far are constraints, not confirmations. The CMB maps themselves are a visual paradox, beautiful and noisy, smooth and speckled, like a weather pattern on the oldest light. Analysts must separate foreground dust, instrumental systematics, and cosmic variance from any truly primordial anomaly. The sky gives only one realization of the random field, so certainty is hard-earned. No compelling bubble collision signal has survived scrutiny, even after years of increasingly sophisticated methods. Analyses place limits on the rate of collisions and the strength of their effects, given the observed smoothness of the CMB. The absence of evidence does not kill eternal inflation, but it narrows the space of simple, loud versions. This is the pattern of the whole series, now at its most extreme and most intellectually honest. Edges keep shifting from material boundaries to informational ones, and each shift changes what exploration means. The Kármán line was a convention, the heliopause was porous, the Milky Way's rim depended on tracers, and the observable universe was a time horizon. Now the edge becomes a boundary between what can be observed and what can only be inferred. The multiverse is not a fantasy of outside space, as if you could fly past the galaxies and find a signpost. It is a claim about disconnected regions produced by known kinds of expansion, extended beyond what we can currently test. Now pivot to brain world ideas, because beyond can also mean extra dimensions rather than extra universes. In some higher dimensional models, our universe is a three-dimensional brawn embedded in a higher dimensional bulk. Ordinary matter and forces are confined to the brain, while gravity can propagate in the bulk. The word brain comes from membrane, and the visual metaphor is deliberate. Imagine a vast sheet, like a thin surface in a larger space, and imagine all familiar particles as vibrations trapped on that sheet. Then imagine gravity as something less confined, able to spread into the surrounding volume. This confinement is not arbitrary in these frameworks, because it can arise from the mathematics of strings and their endpoints. It can arise from how open strings end on brains, while closed strings, associated with gravitons, move through the full higher dimensional space. The result is a universe that feels three-dimensional to particles, yet is not three-dimensional in its full geometry. If gravity leaks into extra dimensions, it changes the meaning of distance and the strength of gravity at short scales. The inverse square law is a geometric statement about how field lines spread in 3 dimensions. In more dimensions, that spreading changes, and gravity could become stronger at small separations. Experiments test Newton's inverse square law down to sub-millimeter ranges, using torsion balances and carefully isolated masses. They search for deviations that could signal extra dimensions or new forces. So far, gravity behaves as expected within measured limits, which constrains many brain scenarios. Brain world cosmology also changes early universe dynamics, which is why it belongs in this chapter about beginnings and boundaries. The Friedmann equations can be modified by extra-dimensional terms, altering expansion at high energies. That can affect inflation, reheating, and the production of primordial gravitational waves. Some brain models propose that the Big Bang was not a singular beginning inside our brain. It could be a collision between brains, or a transition in the bulk geometry that appears as a hot start on the brain. These ideas aim to replace a boundary in time with a process in higher dimensions. The imagery here is stark and abstract, 2 vast surfaces approaching in a dark, higher dimensional arena, then a flash of energy localized on the brain. Even if the picture is only a metaphor, it captures the intent. Trade a mathematical singularity for a physical event. The question becomes whether any trace of that event could survive into observable data. But brain ideas also inherit the same discipline problem as multiverses, and the comparison is instructive. Extra dimensions can be mathematically consistent, yet hard to probe directly. The more freedom a model has, the more it must earn belief through distinctive, risky predictions. Now connect brains back to the series' central hook, because the sky changes again here. If our universe is a brain, then beyond the edge is not farther out in 3-dimensional space. It is a direction that matter cannot take, a dimension we do not move through, even as gravity might. That is a different kind of beyond than eternal inflation, yet the two can interact in serious models. Some scenarios place inflation on a brain, driven by brain motion in the bulk and the energy of their separation. Others imagine bubble nucleation as transitions between vacua in a higher dimensional landscape. The chapter's climax is not a claim that these pictures are true, because certainty is not the tone of the frontier. It is the realization that modern cosmology has multiple, internally motivated ways to produce more reality than we can observe. The edge of space becomes the edge of causal contact, and then the edge of what counts as science. So we have to ask what counts as evidence, without turning the question into pure philosophy or mere rhetoric. Falsifiability matters because it forces models to risk being wrong, and risk is the price of scientific meaning. A model that can explain any outcome explains nothing in the scientific sense. But cosmology also lives with one universe and one sky, which complicates simple slogans about testing. Some hypotheses are not directly falsifiable today, yet can be compared by how well they compress existing data. Bayesian reasoning formalizes that comparison by weighing prior plausibility against likelihood given observations. Bayesian thinking does not rescue unfalsifiable ideas by itself, and it can fail if the model is too flexible. It demands that a model assign probabilities to outcomes, and that those assignments be constrained by data. If a multiverse model cannot define a measure, cannot regulate infinities, or cannot make stable statistical predictions, it fails even as an inference framework. This is the measure problem in eternal inflation, and it is a core risk rather than a technical footnote. If inflation produces infinitely many bubbles, then counting outcomes becomes ambiguous. Different ways of regulating the infinity can change predicted probabilities, which undermines explanatory power. The landscape inherits a similar challenge, because many vacua is not yet a predictive distribution. If there are many vacua, we need a principled way to say which are likely and which are rare. Without that, we observe this because we are here becomes too flexible, and the theory stops constraining reality. Yet the discipline remains, and it is visible in how scientists actually work day after day. They search for bubble collision imprints, for non-Gaussianity, for tensor modes, and for anomalies that would demand new physics. They test gravity for extra-dimensional leakage, and they constrain dark energy's equation of state with surveys. Those surveys are themselves a kind of visual expansion of the sky. Galaxy redshift maps, weak lensing shear fields, and supernova light curves. They turn the universe into a dataset with geometry, growth, and history. Each measurement tightens the range of viable models, even when it does not deliver a dramatic discovery. They also keep the hierarchy of confidence explicit, which is part of the scientific culture at the boundary. Inflation as an early accelerated phase is plausible, because it explains multiple observations with a small set of ideas. Eternal inflation, the multiverse, and the landscape are possible extensions, but they sit further from direct testability. Hold the mysterious tone without drifting into certainty, because the chapter's power is the boundary itself. Beyond the observable universe may be more of the same cosmic web, continuing past our horizon with the same physics and the same slow growth of structure. Beyond that may be regions forever disconnected by expansion, whether from inflation long ago or dark energy now. And beyond that may be a structure we cannot picture in 3 dimensions, even with the best metaphors. A bulk with extra dimensions, where our universe is a surface, and where the word outside finally means something other than farther away. The edge becomes a question about what kinds of space are physically real. Now return to the earlier narrative callback about dark matter, because it anchors the speculation to an unresolved fact we already live with. Dark matter is still the dominant scaffold of structure, shaping galaxy rotation curves, lensing maps, and cluster dynamics. Yet its particle nature remains unknown, even after decades of searches. Any deeper theory that multiplies universes or dimensions must still account for the dark sector we already infer in this one. If new fields or extra dimensions exist, do they provide a natural dark matter candidate, or do they complicate the picture further? The edge of theory is not an escape from existing mysteries. It is where they must be integrated. The same is true for dark energy, which now acts like the universe's slow eraser. It creates a future event horizon and drives cosmic isolation, thinning the accessible cosmos over unimaginable timescales. It turns the question of beyond into a question about what information can survive and what can ever be shared. Imagine the far future sky from within a bound island like the local group. After the last distant galaxies have red-shifted away, the background becomes emptier, and the evidence for a larger cosmos becomes harder to reconstruct. What we call cosmology depends on an era when the universe is still readable. Now pivot towards the next chapter's promise, because the deepest edge is not distance, it is time. If we cannot go beyond the universe in space, can we go beyond its beginning? We have followed edges from air to plasma, from heliosphere to halo, from galaxies to horizons. Here, at the climax, the edge is a limit on causality and testability, where our best equations hint at more reality than we can ever see. The next step is the oldest edge of all, the boundary of the beginning, where even inflation may not be the first chapter. At the edge of space, the sky doesn't end. It changes, becoming a map of what can and cannot be known. And beyond the last light we can measure, the question is no longer what we will find. The question is what we can ever know. At the edge of space, the sky doesn't end. It changes, and the change keeps escalating into stranger questions. Above the last blue haze, the horizon sharpens into a thin curve, and the atmosphere fades into a fragile glow. The sun hardens into white fire, stars appear at noon, and the blackness looks absolute. Yet it is crowded with physics. What feels like emptiness is a stack of transitions, each one revealing a deeper rule set. We have chased edges that were never walls. The Kármán line was a convention, drafted for engineering and flight records rather than nature's own boundary. The heliopause was porous because the solar wind mingles with interstellar plasma in a turbulent, shifting sheath. The galaxy's rim depended on what we measured, whether starlight, gas, or the faint halo of dark matter. The observable universe was a horizon made of time, because light has only had so long to travel. Now the documentary pivots from distance to origin, because the deepest edge is the beginning itself. When we ask what lies beyond the edge of space, beyond stars, galaxies, and even the observable universe, we are really asking what before could mean. The question sounds simple, but it reaches into the definitions of time, causality, and what counts as an event. Start by reframing the Big Bang, because the common picture is wrong. It was not an explosion into empty space, with matter rushing outward from a central point. It was an early, hot, dense state, where space itself expanded and cooled as the universe aged. That distinction matters, because it changes what outside even means. Everywhere was once close, because everywhere was once small. There was no center to fly away from, and no outer shell to reach, because the expansion happened within the geometry. Expansion is the stretching of distances in the metric, not debris moving through a pre-existing void. Even the simplest analogy, dots on a balloon, helps, as long as we remember the balloon's surface has no preferred center. In the earliest moments, temperature and energy were so extreme that familiar matter could not exist as atoms or even nuclei. The universe was a plasma of particles and radiation, with interactions happening constantly, and with pressure shaping how density could clump. As it expanded, it cooled, and the rules of chemistry and structure gradually became possible. The equations that describe that early state work extremely well, until they don't. Run general relativity backward, and density and curvature rise without bound, as if the math is pointing to a breakdown. The singularity appears, not as a place, but as a warning. It is the theory telling us where it stops being trustworthy. A singularity is a signpost of incomplete physics, where our model stops making reliable predictions. It tells us that classical spacetime is being pushed past its domain, like using a map beyond its printed edge. It demands quantum gravity because quantum rules cannot be ignored at that scale. When lengths approach the Planck regime, the very idea of a smooth continuum may fail. So what could replace the singularity? One option is a bounce, where contraction precedes expansion, and the universe avoids an infinite density. Bouncing cosmologies aim to trade a hard beginning for a transition, with a minimum size rather than a zero. The challenge is to make that transition stable and to keep it consistent with what we observe later. Loop quantum cosmology is a specific bounce idea built from quantized geometry. In some versions, spacetime has discrete structure that creates an effective repulsion at extreme density, a quantum pressure against collapse. The collapse halts, then reverses, and the universe re-expands with a new arrow of time. The details depend on how quantum states of geometry evolve, and on how matter couples to that geometry. Cyclic models extend that logic into repetition, with many expansions and contractions. They aim to explain why the universe looks smooth and nearly flat without a unique initial moment, because smoothing can happen across cycles. They also face hard questions about entropy and memory, since disorder tends to accumulate and history tends to leave traces. If cycles repeat, what resets the clock, and what survives from one era to the next? Ekpyrotic scenarios offer a different route, using a slow contracting phase to smooth and flatten the universe. In brain-inspired versions, a collision or interaction triggers a hot start, translating higher dimensional motion into heat and particles. The goal is controlled initial conditions without inflation's open-endedness and without relying on an extremely special starting state. These models must still explain the observed spectrum of perturbations with the right correlations. None of these ideas is a free rewrite of history. Each is a proposal to solve specific problems, like singularity avoidance, horizon puzzles, and the origin of initial conditions. Each must still reproduce the successes of the hot Big Bang, including light element abundances and the precise blackbody shape of the cosmic microwave background. In cosmology, elegance is not enough. Survival requires contact with data. Now widen the scale again without changing the question, because structure is the fossil record of the beginning. Galaxies did not appear from nothing, and they did not assemble randomly in a featureless sea. They grew from tiny early variations that gravity amplified over billions of years, while expansion tried to pull everything apart. The cosmic web is a compromise between attraction and stretching. Those variations begin as quantum fluctuations, unavoidable jitter in fields and energy. In the early universe, expansion stretches them to cosmic scales, freezing them into patterns when wavelengths outgrow causal contact. What starts microscopic becomes a pattern written across the sky, a faint imprint that later becomes clusters, filaments, and voids. The remarkable idea is that quantum uncertainty can become classical structure. We have already met that pattern in the CMB. Its anisotropies are small, but they are not random noise, and they are not merely instrument artifacts. They encode acoustic oscillations, matter content, and the initial spectrum that seeded the cosmic web. The peaks and troughs are a record of sound waves in the primordial plasma. captured when the universe cooled enough for electrons and protons to form neutral hydrogen. This connects the beginning to what we can still measure today. The CMB is not only the last scattering surface, a shell of light from when photons began to travel freely. It is a statistical fingerprint of whatever mechanism set the initial perturbations, including their amplitude, tilt, and possible non-Gaussian features. When we map those tiny temperature differences, we are reading early universe conditions in code. If we want to see earlier than the CMB, we need new messengers and new tracers. Primordial gravitational waves would be one, because they travel almost unimpeded from the earliest moments, carrying information about energy scales and dynamics. Their imprint could appear as B-mode polarization patterns, a subtle curl in the CMB's polarization field. Detecting that curl would be like hearing a faint bass note beneath the cosmic hiss. B-modes are difficult because dust and foregrounds can mimic the signal, and even our own galaxy adds polarized emission. Yet the prize is direct information about ultra-early physics, including inflationary energy scales or alternatives that predict different tensor signatures. A clean detection would not end the debate, but it would narrow the menu of viable beginnings. Another path is 21-centimeter cosmology, using hydrogen's hyperfine line to map the cosmic dawn. It can probe the era before the first stars fully reionized the intergalactic medium, when neutral hydrogen filled most of space. It offers a three-dimensional history, not just a surface, because different radio frequencies correspond to different cosmic times. In that drifting radio whisper, the first heating and the first starlight may leave measurable scars. Next-generation surveys will also map large-scale structure with unprecedented precision. Weak lensing, galaxy clustering, and baryon acoustic oscillations will tighten constraints on initial conditions and growth, and they will cross-check each other's systematics. They will test whether our simplest assumptions survive, including the nature of dark matter and the behavior of gravity on the largest scales. The more precisely we measure structure, the more sharply we infer the past. Even negative results matter because they carve away possibilities. They can rule out loud versions of models, constrain reheating histories, and limit exotic early components that would alter expansion or perturbations. The edge moves when uncertainty shrinks, and sometimes the most important discovery is what the universe refuses to do. In cosmology, silence can be as informative as a signal, but there may be a deeper limit that no instrument can cross. If time itself emerges from a quantum regime, before might be undefined, not merely unknown, because the parameter we call time is part of the classical description. The beginning could be a boundary condition, not an event inside time, and if that is true, our language may be reaching its own horizon. In that case, asking what happened before the Big Bang is like asking what is north of the North Pole. The question assumes a coordinate that stops applying, so it cannot be answered in the usual way. The edge is not a missing chapter. It is the end of the book's language, where grammar fails before imagination does. Now return to the edge of space imagery, because the series began with a sky turning black above Earth. That quiet black was never empty. It was a doorway to layers of regime change, from air to plasma to gravity to horizons. Each layer looked like an ending until measurement showed it was a threshold. The final edge is the same kind of boundary, only more abstract. It is not a wall in space you can reach with engines, and it is not a coordinate you can point to on a star map. It is the boundary of causality, observation, and theory, drawn by what can leave an imprint. The universe may extend beyond what we can see, but beyond what can affect us, it becomes physically unreachable. So the central question resolves in a new form. Beyond the edge of space is not simply more space, and it is not a single border to reality. It is a set of horizons that depend on time, expansion, and the laws we can test. What we call beyond is often just not yet constrained. Each generation pushes that horizon outward, not by traveling farther, but by measuring better. We replace imagined walls with sharper models, then discover where those models fail, and we build again from the fracture lines. The edge keeps moving because knowledge keeps moving, and because nature keeps offering clues in faint, measurable traces. The question is whether the traces eventually run out. The universe may be finite or infinite. It may be singular or cyclic. It may be solitary or one bubble among many. But our best tool for crossing any edge is evidence, and evidence is what turns mystery into map. The deeper the mystery, the more precious the measurement. At the edge of space, the sky doesn't end. It changes. And beyond the last light we can see, the universe gets stranger in a final way. The frontier becomes what we can ever know. We began with a simple ascent and watched familiar cues fall away as the air thinned, the sky darkened, and space revealed itself as a gradient. From the Kármán line to the magnetosphere, from the heliopause to the Milky Way's sprawling halo, every edge we crossed turned out to be a change of regime, drawn by density, pressure, fields, or motion, and sharpened only by what we chose to measure. And when we finally widened our view to the cosmic web, the CMB, and the geometry of space-time itself, the most consequential boundary stopped being a place and became a limit on information carried through time. Across these scales, the pattern held, and it grew more unsettling the farther out we went. The universe does not present us with a final fence. It presents us with horizons. The heliosphere filters particles, but it does not end the interstellar medium. The Milky Way's rim depends on whether you trace starlight, gas, or the dark matter that outweighs them both. Even the observable universe is not the edge of existence, but the edge of what light has had time to